Coming up later in Machine Learning Street Talk, Professor Yann LeCun, the godfather of deep learning.
There's been a lot of people who've been sort of saying there's a limitation to deep learning, let's say, or machine learning more generally, because it's obvious that those things basically do curve fitting, and that only works for interpolation and not for extrapolation. And that kind of dismissal always sounded wrong to me. Would this qualitative difference be in the form of fundamentally different things from deep learning, things that are, like discrete symbolic reasoning or things of that type? And to that, my answer is clearly no. I do not believe that's the case. That's a limitation of supervised learning. It has absolutely nothing to do with deep learning.
Computing on things.
Okay, I put a stop right there.
We also had a fascinating conversation with Randall Balestriero from Meta AI Research.
So I think it's two different things to be able to interpolate or move on your manifold and being in the interpolation regime from your training set.
So is this similar to interpolation?
Well, all of machine learning is similar to interpolation if you want, right? When you train a linear regression on scalar values, you're training a model, right? You're giving a bunch of pairs X and Y. You're asking what are the best values of A and B for Y equals AX plus B that minimizes the squared error of the prediction of a line to all of the points, right? That's linear regression. That's interpolation. All of machine learning is interpolation. In a high-dimensional space, there is essentially no such thing as interpolation. Everything is extrapolation. So imagine you are in a space of images, right? So you have a color images, 256 by 256. So 200,000 dimensional input space. Even if you have 1 million samples, you're only covering a tiny portion of the dimensions of that space, right? Those images are in a tiny sliver of surface among the space of all possible combinations of values of pixels. And so when you show the system a new image, it's very unlikely that this image is a linear combination of previous images. What you're doing is extrapolation, not interpolation, okay? And in high dimension, all of machine learning is extrapolation, which is why it's hard.
Now that was a clip that went out on the Cholet show, and I think I understand now what LeCun meant. He's saying that our intuition of interpolation is only correct in a very low number of dimensions. It's a mathematical impossibility to have statistical generalization in high dimensions. So he's not saying that neural networks are really extrapolating in the sense of continuing the pattern. He's saying our definition of extrapolation, the convex Hall membership, is broken. Machine learning does not and will never work in high dimensions. That's why we've invented so many tricks to reduce the statistical and approximation complexity of problems, just like we do in computer science with the computational complexity of algorithms. LeCun is not saying that deep learning models are clairvoyant. Yann LeCun thinks that it's specious to say that neural network models are interpolating, because in high dimensions, everything is extrapolation. Oh boy. We started thinking about making this show many months ago when Randall Balestriero and Jerome Presente and Yann LeCun first released their paper, Learning in High Dimensions Always Amounts to Extrapolation. And it feels like a lot has happened since then. They do say the mark of an educated mind is being able to change your opinion in light of new evidence. Where we are now compared to where we were then, let's just say I feel like I'm standing on the surface of Pluto. I was initially quite skeptical of this paper, and I was trying to pick it apart, and now it feels like we've done 180 degrees, not only on the way we think about the paper, but how we think about neural networks in general. And we really want to try and impart some of that knowledge with you today in the introduction, which might be quite ambitious, so please bear with us. But, generally speaking, the structure of the show today is going to be a big show. It's going to be a big show. Use the table of contents, skip around a bit. But there's an intro, there's a where we talk about this spline view or this boundary view of neural networks, which I think is very interesting. There's a conversation with Yann LeCun, the godfather of deep learning. And we also speak with Randall Balestriero, who released this beautiful paper about thinking about neural networks in this new way. And we have a debrief as well. So I've not edited the show yet, but it's going to be about 3 hours. Anyway, the show must go on. So as I was saying, particularly speaking with Randall was a revelation. I originally thought that the authors were saying that people shouldn't think of neural networks as interpolators because they thought neural networks were doing something even more sophisticated. But what I came to realize, at least in Randall's case, is he's even more cynical about the behavior of neural networks than Gary Marcus. He doesn't think that they're fitting curves at all. Reading Randall's recent Spline theory of deep learning paper has completely changed the way that I think about their behavior. So his view, basically, is that neural networks recursively chop up the input space into these little convex cells, or polyhedra, conceptually similar to decision trees, but one where the regions in a layer can share information, which means that different faces of these polyhedra will correspond to different hyperplanes set down by different neurons in the neural network, of course, ones which are topologically addressable from that location. So to me, like, this ends the notion that these neural networks are learning smooth data manifolds or performing smooth geometric transformations in the generative setting, which I used to think of as being a kind of diffeomorphism. It also gave me the realization that, at least in inference, each input prediction is representable with a single linear affine transformation, which leads directly to the next realization, which is that the latent space is not homogeneous. It's potentially a different space for every single input example. I just didn't realize that before. Suddenly a lot of the magic of deep learning has vanished, and I see them in the same light as things like decision trees and SVMs in classical machine learning. I mean, probably because I understood those things very deeply. Neural networks have lost a little bit of their mystery, but I think it's a good thing. Reminds me a little bit of this parable of the blind men and the elephant, where, let's say you got 4 blind men around an elephant. One's got his arm around the trunk. Oh, it feels like a snake. One's feeling the tail, or it looks like a rope, or it feels like a rope. One's on the side, or it feels like a wall. And it's a very similar situation with neural networks, that, the experience of these blind men, it's all the truth, but it's not the complete truth. We're all just trying to understand this thing from different angles. Now, anyway, the 2 key challenges in machine learning are, 1, the curse of dimensionality. And as a corollary of that, knowing what to ignore in the input space, because it blows up exponentially with the dimensions. And 2, the extrapolation problem. What happens when you extrapolate outside of the training data? And why does this notion of extrapolation even matter? Well, put simply, it matters because of the implications it has for generalization in deep learning. Now, why do deep learning models work at all? Well, I think there's an incredible amount of engineering which goes into these state-of-the-art machine learning models, which makes them work very well on specific tasks. But it's easy to deceive yourself with neural networks. Literally, everything about your training process and predictive architecture could be leaking domain-specific information into your model. Neural networks are not really blank slate models like we've been led to believe. A lot of human-crafted domain knowledge goes into these models. By the way, this is why Francois Chollet, he talks about this notion of developer-aware generalization, which is being able to generalize to tasks which the developer of the system didn't know about at the time. Now, Weights and Biases is the developer-first MLOps platform. Build better models faster with experiment tracking, dataset versioning, and model management. It provides a platform and a set of tools which you can use for the entire life cycle of your machine learning process. Every team has a reliable system of record for their engineering system, right? Whether it's Azure DevOps for software engineering or Confluence for team wikis. Weights and Biases is your system of record for machine learning. Now, for your quick link and to help out the podcast, head over to onedb.me/MLST. I'm extremely proud, actually, that we've been sponsored by Weights and Biases. I've been a huge fan of what they've been doing since the very beginning. And also, I've been a part of their community forum. They are the one company who, in my opinion, has totally changed the game around what is the highly nuanced process and the kind of multidisciplinary team actions that are required to get machine learning models safely into production. I've been a chief data scientist for a major corporation for the last 18 months or so, and I've always been a big believer in introducing engineering rigor to machine learning and data science. Engineering fundamentals are so important when you bring machine learning systems to production, as is helping data scientists to become first-class citizens in the entire life cycle of model development and deployment. It's almost a shame that MLST has become quite science orientated, because in my day job, I'm an engineer first. I would love to make more content about this stuff. Anyway, Weights and Biases helps you go faster. It makes your team more resilient by increasing your knowledge sharing. It helps you build models which not only have better predictive performance, but are more safe and secure. Weights and Biases gives you better management information, allowing your company to make better decisions and build data products with greater transparency than ever before. And critically, because Weights and Biases orchestrates the entire machine learning process, your models are reproducible and important decisions are immortalized. This fine level of control lets you set guardrails where you need to and reduce friction wherever possible. I've designed many ML DevOps systems over the years, including when I worked at Microsoft. The technology has really come of age now, and I think you should be using a platform like Weights and Biases to help you train your machine learning models and to get them into production. Reproducibility has always been one of the biggest problems in machine learning, and the reason for that is that these systems are quite brittle, frankly. Their runtime characteristics depend strongly on the vagaries of the training regime, the choice of hyperparameters, even the hardware that they were trained on. You always get into this syndrome where it works on my machine, but I can't put it into production because I've got no idea how to recreate this thing somewhere else. I work in a highly regulated industry, and we often need to wind the clock back to try and understand how a model was created, which decisions were made, and possibly go back later to reason about a model's behavior. This is precisely what Weights and Biases does. Now, it's completely free for academics, and it's simple to get started. You just have to add a few lines of code. So what are you waiting for? Remember to click on our special link because it helps us out. That's 1db.me/MLST. We are so grateful for the sponsorship from Weights and Biases. And also feel free to get in touch with us if you're interested in sponsoring the show. It'll help us scale up the operation a little bit because at the moment I'm doing all the editing and it takes a lot of time. Anyway, thank you very much.
Randall's other recent work demonstrates that a large class of neural networks, including CNNs, ResNets, RNNs, and beyond, those that use piecewise linear activation functions like ReLU, can be entirely rewritten as compositions of linear functions arranged in polyhedra or cells in the input space. It's a high-resolution slice and dice into linear forms, like a fruit ninja set loose on a marching cubes algorithm, such as k-means clustering, matched filter banks, and vector quantization, which in plain English means locality-sensitive clustering. It also provides new insight into the functioning of neural networks themselves. For example, with this view, what a neural network is doing is performing an input-sensitive lookup for a matching filter, and then computing a simple inner product between that filter and the input signal. If that doesn't shed light on Francois Chalet's characterization of neural networks as locally sensitive hash tables, then I don't know what will. Another cool thing to come out of Randall's work was a geometrically principled way of devising regularization penalty terms, which can improve neural network performance by orthogonalizing the placement of those latent hyperplane boundaries to increase their representational power. In short, looking at neural networks through this piecewise linear kaleidoscope, if you will, is opening new avenues of technical understanding and exploration. Now, we spoke with Yannick about this as well, and he commented that he had looked into these polyhedra, which he called ReLU cells, in his own research. While he agreed that the boundaries between them are not technically smooth, there are so many of them, combinatorially many possible polyhedra in fact, since each can be defined by any combination of topologically addressable hyperplane boundaries. There are so many, Yannick thinks that neural networks can make them effectively smooth by arranging them so that they change very little from neighbor to neighbor. This insight came from his work in adversarial examples, where the name of the game is to perturb the input as little as possible to the nearest polyhedron with a different class. Anyhow, for me, Randall's work has transformed the way I think about neural networks. I know what they're doing at a much deeper level now. Each layer of a neural network contributes a new set of hyperplanes, and the ReLUs act to toggle the hyperplanes in an input-sensitive way. Every layer, indeed every neuron in the network, not just the final layer, participates in placing flat decision boundaries defining a honeycomb of affine cells. Each input signal will fall into one of these cells and be transformed by the combined affine transformation of every neuron it activated. I also used to think of a single unified latent space at each layer. However, it seems obvious that any particular input will toggle in an input-specific way a set of hyperplanes by virtue of the ReLUs it does or does not activate. Therefore, different populations of input samples will reside in different latent spaces at any one layer, defined by the activated set of hyperplanes. So it seems to me that instead of having a unified latent space, we have input-specific latent spaces, plural, at each layer. There is also the matter of whether classifiers are even learning the data manifold at all. I have my doubts. They may be learning predictively useful aspects of the manifold. However, neural network classifiers are optimized to find class boundaries, and any structure between boundaries can be ignored. The idea that learning boundary manifolds necessarily means learning intrinsic connection manifolds is where I'm really struggling now. I can't convince myself that optimizing for separation will give the same outcome as optimizing for connection. For example, training the same neural network in two different ways, one for classification and once for decoding or generation, will result in very different network weights and latent structure. It's even more difficult to accept now that I'm thinking of these manifolds as piecewise linear, where what the neural network has learned is combinations of separating hyperplanes that chop the space into single-class polyhedra. After all, there is nothing in the objective function which cares about the structure within a polyhedra. As long as the class is correct, we're good. Nor is there anything necessarily optimizing for global manifold structure beyond just efficient and parsimonious use of the available parameter space and whatever prior structure was hard-coded by humans in the network constraints and topology itself. Randall commented in the interview that in high-dimensional spaces, you can easily separate everything, but your generalization performance might be bad. So you want to trade off separability with dimensionality. He thinks the merit of deep neural networks is being able to find a nonlinear transformation which retains separating hyperplanes while reducing dimensionality enough to confer generalization power.
I mean, I couldn't help but notice that everything in the machine learning world is linear. All the popular algorithms are linear, and any non-linearity is a trick. I mean, we just apply some non-linear transformation to the data before running it through our algorithms, just like how it is in support vector machines or kernel ridge regression and Gaussian processors. Deep learning models are no different. We're just placing these ReLUs all over the input space to slice it and dice it. Let's think about this. I mean, what is the simplest mathematical model? Linear, right? What's the next most simple one? Piecewise linear. So machine learning hasn't even evolved yet to the second order. I mean, neural networks in their contemporary usage only include the minimum possible nonlinearity of piecewise linear. If they didn't, an entire neural network model could be described as one monolithic linear function with a single transformation matrix. This view, I think, should give you a cleaner and analytical view of neural networks. Now, there are some reasons, in my opinion, for the tendency towards linear. I mean, computability is one of the reasons, but almost every part of mathematics favors linearization, whether it's Newton's method or calculus or linear algebra, solving PDEs, plenty of other examples. So it shouldn't come as a huge surprise. Not only that, the function space of nonlinear functions is exponentially larger. And remember, in machine learning, the big challenge is to reduce the size of the approximation class. So what about boundaries? Now, the purpose of every ReLU cell is to define a boundary in the ambient space to chop off what is no longer required. All you have is a linear separating hyperplane, and downstream you work out the distance from the hyperplanes that you're on the right side of, the ones that didn't get chopped off. So the magic of neural networks is actually learning what to ignore in the ambient space. Now, I think a problem with my previous intuition is that, like most people, I imagined neural network latent space is a bit like a UMAP or a t-SNE projection plot, and this leads us to misunderstand their behavior. The latent space that these examples get projected into is not homogeneous. Depending on which cell you fell into in the input space or the ambient space, a different affine transformation will be applied, sending you to a different region of the latent space. So the latent space is kind of stitched together like bits of a cosmic jigsaw puzzle in the ambient space. And then when you run UMAP on the latent, you see all of the clusters, but you'd be forgiven for thinking that it was performing some kind of smooth diffeomorphic transformation of the entire input space and successive layers in the neural network, or even learning the topology of the data manifold. I think it's much better to think of neural networks as quantizing the input space, much like a vector search engine does, using locality sensitive hashing. Now, imagine a classification problem on the Cartesian plane where the upper right and lower left quadrants are blue and the upper left and lower right quadrants are orange. Now, as a minimal example, if we trained a single layer 4 neuron ReLU neural network to fit this, it will fit 4 diagonal hyperplanes, 2 of which are reflected versions of the same hyperplane. Now, by the way, you can play with this on the TensorFlow Playground, which we think is probably one of the best tools for building strong intuition on how neural networks work. Now, what it does is it shows you how the ambient space is being effectively subdivided by all of these addressable hyperplanes. But this quadrant example is unintuitive in the tool because getting your head around how the ReLUs act together to combine these hyperplanes to carve up the ambient space isn't immediately obvious. Now, when you run the tool on a more complex example, so for example, a spiral manifold, you'll now see the artifacts of these hyperplanes everywhere. When these piecewise linear chops are composed together in the second layer, we get a decision surface in the ambient space which can appear smooth given enough pieces, but it's actually a composition of piecewise linear functions. Now, as you can see, it's just chopping up the input space in every neuron in the first layer, each one with a different angle and translation. And when you get to the second layer, it's chopping up the space in a more sophisticated way by composing together the chops from the previous layer. Now, the first thing to realize here is that for each test input example, and every example in its vicinity, its class projection is definable with a single affine projection. There's no continuous morphing going on here. It's more like a jigsaw puzzle being pieced together to form many parts of a bigger ambient space. Now, oftentimes we see negative weights, which actually allows the hyperplanes to combine in interesting ways to kind of partially cancel each other out to allow more complex decision boundaries. Any hyperplane can be reused by multiple other neurons, whichever neurons it can reach via some topologically addressable pathway. Every hyperplane can be the face of multiple polyhedra in the ambient space. This is how they share information. And it should be obvious by now that there are 2 to the n addressable polyhedra in the ambient space, where n is the number of neurons. Now, we also observe that the neural network is only capable of slicing and dicing the input space with flat planes. The only smooth nonlinearities enter the picture here, where we as data scientists linearize the data by performing some smooth nonlinear transformation before it even enters the neural network, much like is the case with other machine learning algorithms. Now, even on the spiral dataset example, the quickest way to make the neural network fit the data is to effectively linearize the data by applying a nonlinear transformation before it even gets in. Now, we also played around with this kind of contrived circular manifold dataset where there's a ball of data encompassed by a circle around it, and it's possible to do a better job on that with one ReLU neuron, right, but with 2 nonlinear transformations of the input dataset. Rather than fit this huge bunch of piecewise linear ReLUs on the ambient data. I mean, it should be obvious, right? But this idea that you don't need feature engineering in neural networks, I think, is nonsense. Now, given how obvious it is that neural networks are just chopping up the input space with these piecewise linear functions, it begs the question, how could they possibly extrapolate in any meaningful way, right? Especially in the general setting. And But by the way, when we say extrapolation, we're talking about this more general sense of continuing the pattern, not the convex whole notion in the given in the paper.
Regarding these piecewise linear functions, I remember an impactful moment from more than 20 years ago in grad school. A visiting professor who had multiple science and nature publications, a pinnacle of academic achievement, was sharing his insights on how we students might also extract such papers ourselves from nature. And he was showing figures from his paper, and they all had two things in common. First, they depicted very simple relationships that were previously undiscovered, okay? And second, all the fitted models were piecewise linear. He even explicitly commented along the lines that, of course, there's some underlying smooth, nonlinear relationship, but absent a solid theoretical model of that, which is often going to be the case for new discoveries, you're better off with simple, piecewise, linear models. I guess when in doubt, Occam's razor always makes straight cuts. And now it's clear to me that the successful deep networks of today are following that advice. If you've ever wondered why piecewise linear activation functions are dominating the field, maybe it's because they've abandoned all pretense at finding smooth, nonlinear models and are keeping it simple by fitting piecewise linear models, albeit at machine scale with billions of parameters. Randall's spline work makes that bit of philosophical insight brutally clear, in my opinion. It conjures a scene of Darth Vader, that cybernetic warlord towering over a growing neural network saying, "Embrace your hyperplanes." Now, I've always been skeptical and often remind us of the limitations of today's machine learning. I'd say things like, ML isn't magic learning. But for a moment, I too allowed myself to become deluded into thinking that they are creating some kind of non-linearity beyond piecewise linearity. But ReLU is by far the dominant activation function because it stops pretending at anything other than piecewise linear. Just stick in a flat boundary threshold and a line. A neuron puts in a hyperplane and then lets the rest of the network chop more as needed. All the success of neural networks seems explained by piecewise linear functions. I also find it intriguing that our own brains, our own wet neural networks, have somehow gained access to smooth, nonlinear imagination. Just look at the laws we've defined in physics. Many exhibit nonlinear but smooth structure. On the other hand, neural networks chop up the input space with flat boundaries and sharp edges. How can we possibly expect them to learn or discover the kinds of smooth relationships that seem fundamental to science and reality?
All feature engineering and representation learning and machine learning is about finding these interpolative representations. Now, I saw a really interesting example of this when I was reading Francois Chollet's book recently, and he spoke of pixel grids of watch faces, right? Now, they're not interpolative in the ambient space. If you take the average of two of these images, you'll just get 4 faded clock hands on top of each other, right? Superposed, not very helpful. But however, if you represent the hands with Euclidean coordinates, then the problem becomes more interpolative, but you're still not all the way there. The average of 2 points of interest doesn't fall on this intended circle manifold that we're interested in. It would be interpolative if we use some relevant distance function, which was some geodesic interpolation. If we encoded the problem using polar coordinates, then it becomes linearly interpolative, right? The problem is solved, and you can generalize perfectly to any new clock face. But, in that case, you wouldn't even need a neural network. And the kicker is that we as data scientists would have to figure this out ourselves, right? The neural network wouldn't be particularly efficient at doing so, especially if we, the data scientists, didn't feed in the relevant nonlinear transformation before it went into the to the model. So anyway, if there exists a non-linear transformation of this problem, then which makes it interpolative, then we can say in some sense that it's got a lower intrinsic dimension. So crucially, deep learning models, they can be understood as unconstrained surfaces. They do have some structure coming from their architectural priors, but that structure only serves to restrict the search space to a smaller space of unconstrained surfaces. It doesn't provide the kind of inductive prior that would enable stronger generalization. A model architecture does not contain a model of the domain, except in the extremely restricted sense of injecting priors such as, translational equivariance in convolutional neural networks. If you want to generalize in a more systematic fashion, you either need a model with a strong inductive prior or a model which doesn't operate by empirically slicing up the ambient space, like a deep learning model does. A discrete symbolic program would be an interesting alternative. I mean, just imagine the program y equals x squared. It generalizes to any arbitrary number, right? Because it's highly structured. You can fit it with 3 training points, and once fit, it'll generalize to anything, even things that are outside of the training range. But the kicker, of course, is that you wouldn't know which curve to use if you only saw 3 points in the first place. Now, let's think of another example, and imagine a discrete staircase space. So in this particular example, an unconstrained curve gives you complete garbage, but a structured model with the correct priors, it can still be a curve, will generalize in the extrapolation regime. And this prior basically means that you need to encode it or linearize it before it even gets into the neural network. In both cases, you're making the neural network work extremely well for a specific thing, but not very well for generalizing between new tasks. So anyway, when we say that deep learning models generalize via interpolation, what we're really saying is that these models that we're using today, they work well with data that's within the training distribution of the problem, right? A problem that's intrinsically interpolative, but they won't generalize systematically to anything else. You won't generalize when looking at problems that are not interpolative in nature and problems that are outside the training distribution. So why do we talk about this binary notion of extrapolation? Well, the problem with the binary convex hull notion of extrapolation is that we're promoting this idea that the moment an example falls epsilon outside the hull, that the prediction qualitatively changes. Instead, I think it would be more of a distance question, right? Which is to say, the further away you get from this convex hull, the greater the uncertainty. I mean, it's not like you fall off a cliff when you step outside the convex hull. Your approximation of the latent manifold remains valid for a little while, although it will quickly degrade as you move further outside, unless your model has some strong structural prior that matches the regularity of that latent manifold. So this brings up an important point, right? The relevant question is not whether you're inside or outside the convex hull. It's how far you are from the nearest training data points. If you're outside the convex hull, but you remain close to the training data, then your model remains an accurate approximation of the latent manifold. And even if you're inside the convex hull, you're in a region that wasn't densely sampled at training time, right? Where there's no nearby training points. Your unconstrained model may not accurately approximate the latent manifold, so inside or outside doesn't really tell you very much. It's all about the proximity. You're performing local generalization, and the quality of your ability to generalize to new situations depends entirely on their proximity to known situations. However, if you're dealing with training data that is densely sampled within a certain region of the problem space, then the question, can I generalize here, becomes approximately equivalent to, is this inside the convex hull or outside? Now, the whole point of feature engineering is to make data sets interpolative. Either us data scientists design the features by hand, or neural networks learn them as part of the training process, in big air quotes for the podcast listeners. So, I think when folks make the argument that machine learning models generalize via interpolation, or that computer vision data sets, that they're interpolative, what they mean is that there's an encoding space for which the problem becomes interpolative, or there exists a non-Euclidean pairwise distance function between the instances that makes the problem interpolative, which is basically the same thing. So, if it's possible to do this, then you can say that the problem is intrinsically interpolative, but your current representation of the problem is not. So the key endeavor in machine learning is to find better representations which reveal the interpolative nature of the problem. Now, you might just cynically write off this paper as being a trivial finding, right? You know, it seems trivial that the pixel space is not linearly interpolatable. It's something that we've known about for decades. I mean, that's why computer vision engineers in the 1980s would write feature detectors to create an interpolative space for machine learning algorithms to work on, right? If you take any two images and you interpolate between them, what do you get? You just get a faded copy of both. Everyone in the field has known about this for decades, right? That examples are not interpolative in their original encoding space or their pixel space. I think the most important thing, though, is that this paper also shows that the models are not interpolative in their latent space either. That's a shocker. Now, what does Randall say about all of this? Well, Randall Balestriero thinks that the steel man for this interpolation argument would be, well, what if you had very low dimensional kind of like approximation of your data with very few factors of variation, which could be easily linearized in the latent space? Then it might be interpolative. Randall thinks that the very concept of interpolation, I mean, it was defined about 50 years ago to describe these very small models with very few factors of variation, and they're just not relevant today, right? They showed in their paper that even in the relatively small latent space on a popular neural network classifier, interpolation does not occur. He thinks that most people think of interpolation by kind of conceptualizing their data into a few important latent factors. You might have dogs, for example, and they might exhibit a latent color, and a new color might be an interpolation between observed colors. But these guys think that we need to have an entirely new definition of interpolation. I think the main purpose behind their paper, according to them, is to show that even though the intuition that people have of interpolation works well in low dimensions, it falls down completely flat on its face in higher dimensions. Actually, the probability of your test data being in the convex hull of your training data is near zero past a certain number of dimensions. So the current definition of interpolation, which is to say like this notion of convex hull membership, it's too rigid to think about how interpolation works in neural networks. So Randall thinks that any new definition of extrapolation should be directly linked to generalization itself. This is what they're trying to get at. This is a clip from our show with Professor Max Welling.
The first thing I want to say, there is no machine learning without assumptions. It just basically, you have to interpolate between the dots. And to interpolate means that you have to make assumptions on smoothness or something like that. So the machine learning doesn't exist without assumptions. I think that's very clear. But you know, clearly it's a dial, right? So you can have, on the one end, you can have problems with a huge amount of data. It has to be available clearly. And there you can dial down your inductive biases. You can basically say, let the data do most of the work in some sense.
Now, I think it's a good thing to build intuition about machine learning principally as an interpolation problem, right? So we're given the training data and we need to cleverly interpolate between the training examples to reason about the statistical context of the test examples. This is what machine learning is in a nutshell. Actually, a researcher friend of mine from Meta AI research in Silicon Valley, a guy called Dr. Thomas Lukes, he published a paper a couple of years ago called Interpolation of Sparse High-Dimensional Data, and he showed that it was indeed possible to perform competitively with multi-layer perceptrons for a regression problem using pure-play interpolation methods like Voronoi and Delaunay triangulation and Spline methods. I mean, think of creating simplexes of the nearest neighbors around your training data and then averaging the results together. This simple method works remarkably well up to about 30 dimensions. I mean, obviously, eventually it gets deranged by the curse of dimensionality, but as we'll discover slightly later, neural networks might have a slight advantage over pure play simplex interpolation just because they work principally by figuring out boundaries of the input space to exclude. So, you know, if you're on the zero side of the ReLU, that is. So that helps a lot in high dimensions when you have a poor sampling density in a particular region of the input space. But anyway, if you do principally think of machine learning as being an interpolation method, it raises some interesting ideas. You know, Thomas said to me that the crux of the problem is that we're trying to approximate a function that has spatially unique behavior in more than about 20 or so dimensions. Like in that case, it's hopeless. There's no question about it. He says that you can increase the data density, like in 100 dimensions, but to get a grid with 10 points on a side, which is to say 10 to the power of 100, there aren't enough protons in the universe that could convexly cover it. So Thomas concluded by saying what this means is that everything that we do successfully approximate now with millions or billions or even trillions of data points, which accounts for a lot of the successes in machine learning, these data sets only have spatially novel behavior in very few dimensions. Right, or a varying gradient in very few dimensions, 16 or fewer. If we suppose that the true function has a varying gradient in more than that many dimensions, there's simply not enough data in the world to approximate it. The mathematics here is unequivocal. So what actually happens when the test examples are outside the convex hull of the training data? What happens when we're in an extrapolative regime? Well, it's increasingly impossible in high dimensions for the training set to be statistically representative of the test set. Test set instances will often distinctly differ from anything that we've seen during training. In machine learning, the test set will never fully characterize the problem that we're interested in. So in high dimensional settings, features are often linearly correlated as well, which makes it challenging to know what information to use and what to discard. This is another fundamental problem of machine learning. Many machine learning approaches depend on modeling these local statistical relationships between the training samples, but in high dimensions, the probability of a new test example being in the convex hull of the training data goes to zero extremely quickly. So making machine learning models work in an extrapolative regime necessitates the introduction of inductive biases, which are a way of adding a kind of enforced smoothness to the model predictions.
So if you hit the right bias, then it can be beneficial. If you impose the wrong bias, then it's going to hurt you. And this is a well-known trade-off. So of course, the whole endeavor of machine learning is defining the right inductive biases and leaving whatever you don't know to the data, and then basically learning to focus your models on the data that you're actually seeing.
This is how we stop models from fitting the noise in the data or going completely haywire outside the convex hull of the training data. Extrapolation requires that sensible answers are given for all of the elements of the input space, even in regions not seen during training. And in particular, those within the convex hull of, let's say, some hypothetical infinitely sampled training data set. Now, what we do in neural networks, and in many other machine learning algorithms for that matter, is we just take a bunch of parameterized basis functions and we stack them and we fit them to our training data until it's well described. The most important considerations for interpolation are the smoothness and robustness of these models, right? We want our models to produce gradual changes between the training points. Points outside the training set should be handled with great care, but what exactly that means depends greatly on the problem. In order to even know that we're in an extrapolative regime, the basis functions must be based near to the training examples. Typically, neural networks do not behave sensibly in regions where there's no training examples, right? Because their learned basis functions have been localized around the training data in the ambient space. It's also worth noting that extrapolation and interpolation are two completely different regimes. Optimizing for one typically means being worse at the other. Now, Randall said that the boundary view of neural networks is very clear in the discriminative setting. You only need interpolation to try and understand how neural networks work in the generative setting. This is a key point. In the generative setting, when you interpolate the latent, we see at first glance what looks like geometric morphing, right? Looking at this, you'd be forgiven for thinking that we're traversing some smooth latent manifold, but on closer inspection, it's not geometric or diffeomorphic at all. It's more of a fuzzy, high-resolution fade-in. Now, one commonly used visual argument for the manifold hypothesis is the MNIST digit interpolation in a generative model. Our own investigation shows that there's a degree of cherry picking in some of the visual examples used to demonstrate this. It's not actually hard to stumble across cases where purported manifold interpolation is no better than ambient space linear interpolation. There are many examples where latent space interpolation gives superposed and fuzzy intermediate representations and even crisp images, which which are unrecognizable. The blur and cutting and gluing which is apparent on these images show that it's definitely not a diffeomorphism in the ambient space. And even though the interpolation path is continuous in the latent space, it's questionable whether that path is semantically relevant to the classification task at hand. Just think of the mean value theorem. It tells you that if you take the value of any continuous function at 2 points, right, you can also find a point between them where the function hits the average of those values. So in other words, any continuous function produces a manifold, but that doesn't tell you anything interesting about the function beyond what we already know, right, that it's continuous. Now, I'm not so sure that these manifolds are even smooth. When we're talking about smoothness, we're only talking about local smoothness and inside the polyhedra's convex hull. It's linear, right? But there's no smooth surfaces or manifolds anywhere to be seen. For any particular node in a neural network, it's actually a linear function of a subset of the upstream linear functions, right? Very much like a decision tree, but with information sharing. Now, another often used visual aid is this idea that a neural network is effectively uncrumpling and smoothing the ambient space, much like you would do with a sheet of paper, with successive transformations in the layers of the neural network. Keith and I previously agreed with this view of neural networks as progressively kind of flattening out the paper, but it now seems to us like they may instead be progressively inserting planes aligned to the facets of the paper ball to chop out locally affine polyhedra or cells to cover the paper's polyhedra. So for us, this is an entirely new way to think about neural networks. Okay, so in a way, this is a new parlor trick, right? Do you remember that thing, the game of life, Conway's game of life? It looks like the shapes are smoothly morphing, but they're actually toggling pixels with discrete rules. Gary Marcus talks about the parlor trick of intelligence, but isn't it ironic that there are more parlor tricks going on than most people realize? Namely, that rather than doing smooth geometric morphing via interpolation, these networks are actually chopping up and composing linear polyhedra. Now, if you interpolate between two latent classes, it might traverse several polyhedra in the intermediate space. Along the way, it would pick up characteristics from all of those polyhedra. Some of the black regions are impossible regions, so it's not possible to get there from the latent space, which is very, very interesting. You only see the illusion of continuous morphing, where the neighboring cells are very small and very similar. This is Professor Michael Bronstein.
I like to think of geometric deep learning as not a single method or architecture, but as a mindset. It's a way of looking at machine learning problems from the first principles of symmetry and invariance. And symmetry is a key idea that underpins our physical world and the data that is created by physical processes. And accounting for this structure allows us to beat the curse of dimensionality in machine learning problems.
So what is the manifold hypothesis? Well, natural data falls on smooth manifolds. The manifold hypothesis states that real-world high-dimensional data lie on low-dimensional manifolds, embedded in the high-dimensional space. When people invoke this hypothesis in a machine learning context, they're generally suggesting that neural networks are actually learning this data manifold, which we now find quite hard to believe, frankly. At best, we think they're learning some approximate aspects of it. So essentially, all machine learning problems that we need to deal with nowadays are extremely highly dimensional. Even basic image problems live in thousands or even millions of dimensions. Now, I think most people have this intuition of convex hull membership, which is to say, in 2 dimensions, as you sample more and more training data, the convex hull eventually fills the entire space. But the kicker is that in higher dimensions, the space is so vast, this will never happen. High-dimensional learning is impossible due to the curse of dimensionality. It only works if we make some very strong assumptions about the regularities in the space of functions that we need to search through. The classical assumptions that we make in machine learning are no longer appropriate. So in general, learning in high dimensions is intractable. The number of samples grows exponentially with the number of dimensions, and the curse of dimensionality refers to the various phenomena that arise when analyzing and organizing data in high-dimensional spaces that do not occur in low-dimensional settings, such as the 3-dimensional physical reality of everyday experience. Now, the common theme of these problems is that when the dimensionality increases, the volume of the space increases so fast that the available data becomes sparse, and this sparsity is problematic for any method that requires statistical significance. In order to obtain a statistically sound and reliable result, the amount of data needed to support the result grows exponentially with the dimensionality. So, the curse of dimensionality in a nutshell is that the probability of a new data point being inside the convex hull of your training data decreases exponentially with the number of dimensions. As an example, to estimate a standard normal density in 10 dimensions with a relative mean square error of 0.1 using an efficient non-parametric technique would require more than 800,000 samples. Now, in the last show, we discussed geometric deep learning in great detail, and in some sense, extrapolation and the curse of dimensionality are analogous. The reason that these folks wanted to combat the curse of dimensionality was they wanted to build models which could extrapolate outside the training range using geometrical priors.
I think it's possible to build understanding of the curse of dimensionality through visual analogy to familiar lower dimensional shapes, such as circles, squares, balls, and cubes. Imagine perfectly sampling an entire space with a regular grid. This would partition space into squares or cubes or hypercubes with a sample in the center of each. Now imagine around each sample a disk or ball or hyperball representing that point's region of nearness or influence. And let's ask, how much of the total volume of that point's grid cell is actually near the sample? The answer is a fraction, which diminishes faster than exponentially with increasing dimension. First, think of the 2D case, a disk or 2-ball with diameter 1 inscribed in a square or 2-cube with sides of length 1. In each corner, we of course have a dart-shaped chunk that isn't covered by the disk. A trick to think about this, which I think will help in higher dimensions, is to imagine scanning a line segment along one dimension from side to side. At the edge of the square, none of the segment is covered by the disk. At the very center, the entire segment is covered by the disk. And then, as it scans towards the other edge of the square, the covered section begins shrinking and then rapidly falls to 0. The total coverage then is just the sum over that scan. In 2 dimensions, that is just the area of a disk with diameter 1 and is about 79%. Extending to 3 dimensions, imagine a ball in a cube, and we scan a square from one face through the ball to the opposite face. As it passes the center, we have our familiar inscribed disk in a square. This is already missing the corner darts, and as we scan towards the edge of the cube, the darts expand and surround the disk as it shrinks to 0. So by adding a 3rd dimension, we've lost even more coverage, and the volume of a diameter 1 ball is only 52%. In fact, if we continue on to higher dimension, the volume of a diameter 1 hyperball decays faster than exponential, factorially fast, in fact. The volume decays so fast that even if we allowed for sampling with the best possible densely packed balls, theoretical work on hypersphere packing tells us that the volume occupied by optimally packed hyperballs would still decay at least exponentially with increasing dimensions. This is the curse. As dimensionality grows, space expands exponentially, points grow further apart, and the volume near each point vanishes. In this episode, our guests argue this curse dooms traditional concepts of interpolation, even if we allow for the high-dimensional transformative power of deep neural networks.
Yeah, so the curse of dimensionality, it refers generally to the inability of algorithms to keep certifying certain performance as the data becomes more complex. And data becoming more complex here means that you have more and more dimensions, right? More and more pixels. And so this inability of like scaling. Basically, it's like it really says that if I scale up the input, my algorithm is going to have more and more trouble to keep the pace. And so this curse can take different flavors, right? So this curse might have like a statistical reason, in the sense that as I make my input space bigger, there would be many much exponentially more functions, real functions out there that would explain the training set, that would basically pass through the training points. And so the more dimensions I add, the more uncertainty I have about the true function, right? So I would need more and more training samples to keep the pace. The curves can also be from the approximation side, right? So in the sense that the number of neurons that I'm considering to approximate my target function, I might need to keep adding more and more neurons at a rate that is exponential in dimension. And the curves can also be from the computational side, right? The sense that if I keep adding parameters to my training model, I might have to optimize, to solve an optimization problem that becomes exponentially harder. And so you can see that you are basically bombarded by by all angles. And so an algorithm like, here in the context of statistical learning or learning theory, if you want, having a kind of a theorem that would say, yes, I can promise you that you can learn, you need to actually solve these three problems at once, right? You need to be able to say that in the conditions that you're studying, you have an algorithm that it does not suffer from approximation, nor statistical, nor computational curses. So as you can imagine, it's very hard, right?
Today is a big day here at Machine Learning Street Talk. We have invited one of the godfathers of deep learning on the show, none other than Professor Yann LeCun. Machine learning royalty, he is Meta Chief's AI scientist and a Turing Award winner, which I don't have to tell you is a big deal. Widely recognized as the Nobel Prize of Computing. Yann LeCun was born in the suburbs of Gay Paris in the 1960s. He received his PhD in computer science from the modern-day Sorbonne University in 1987, during which he proposed an early form of backpropagation, which is, of course, the backbone for training all neural networks. Whilst he was at Bell Labs, he invented convolutional neural networks, which again are the backbone of most major deep learning architectures in production today. He has been at New York University since 2003, where he is Silver Professor of Computer Science and Neural Science. Apart from being perhaps the most known researcher and main ambassador for deep learning, he has championed self-supervised learning and energy-based models. In 2013, he created the hugely prestigious ICLR conference with Yoshua Bengio.
A lover
True
of the green
words.
screen, I see.
Well, normally, when I use Zoom, I put a substituted background.
Well, Tim could do it for you in post if you want.
If you want.
Well, it's never a very good cutout. I did hack together some Python code to do it, but there's no substitute for the real thing.
I attempted to do this. I'm running Linux, so I attempted to do this by, making like a fake video driver, but it introduces a little bit of delay. So,
Professor LeCun, it's an absolute honor to have you on the show. When I first started MLST with Yannick and Keith and Connor, we were discussing how long it might take to finally get the main man himself on the show. You've been a huge inspiration to all of us here on MLST, and also you've inspired millions around the world to embark on, successful careers in data science and to dream about what might be possible with artificial intelligence. Now, we've read your recent paper, Learning in High Dimensions Always Amounts to Extrapolation, which you co-authored with Randall Balestriero and Jerome Pesenti. Let's get straight into it. So, we were wondering, why did you write this paper, basically? We were thinking whether interpolation and extrapolation is a useful dichotomy. I mean, at the end of the day, we measure performance of learning methods with accepted metrics of predictive performance, such as accuracy. So suppose everyone adopts your linear convention, which is a convex hole membership. and concludes that high-dimensional learning is always extrapolation. How is that useful? What do we do with this knowledge? And vice versa, suppose that everyone adopts a different definition and concludes that learning is always interpolation. What difference would that make in machine learning research and practice? So, in sum, why is it important to distinguish whether we're predicting by interpolation or extrapolation?
Okay, very interesting question. So first of all, this is maybe the first time you have me as a interviewee, but I've watched a bunch of your videos, so you've had me as an audience at least,
Wow,
which
cool.
I find really interesting, actually. So the answer to your question is, the whole point of the paper is to show that this notion of interpolation versus extrapolation is not useful, essentially. There's been a lot of people who've been sort of saying there's a limitation to deep learning, let's say, or machine learning more generally, because it's obvious that those things basically do curve fitting, and that only works for interpolation and not for extrapolation. And that kind of dismissal always sounded wrong to me, because in high dimension, geometry in high dimension is very different from what the intuition that we form with, curve fitting in low dimension, right? So part of the motivation for this paper was to kind of perhaps help some people gain some intuition about what really is taking place in machine learning in high dimension, and also kind of dispel the myth essentially that machine learning and deep learning in particular only does interpolation. Of course, it depends a lot on your definition of interpolation. So here we adopt a definition which is an obvious and simple generalization of interpolation in low dimension, which is that you interpolate when a point is in between the points you already know, and the generalization to this in high dimension is you interpolate when a new point is inside the convex hull of the points that you already know. Now, what you have to realize, of course, is that in high dimension the volume of that space is actually tiny compared to the overall volume of space that would be filled, in high dimension. And so that's kind of the intuition behind this paper, that any new point, regardless of how you sample it to some extent, any kind of reasonable ways to sample points, in high dimension, new points are always going to be outside the convex hull, or almost always going to be outside the convex hull of existing points. With that definition.
Interesting.
Now, there's a second part to your question. Is that, is there a more sensible definition of interpolation and extrapolation? And the answer is probably yes. The paper doesn't address it, but there are other definitions of hulls, if you want. They're not necessarily convex hulls, or they're not necessarily the usual type of convex hull. So, for example, there is a definition of a hull for a cloud of points that would be the smallest paraboloid, or ellipsoid, I should say, actually. The smallest ellipsoid that contains all the points, right? So some points are going to be on the surface of the ellipsoid, but most of them are going to be inside. And for this type of, and so now your definition of interpolation is that is a new point likely to be inside the ellipsoid of a previous point or outside? And the answer to that is probably very different from the one in the paper, in the sense that it's very likely for a lot of natural data, new points are likely to be inside the containing ellipsoid. So it very much depends on what you mean, but it's just that the notion of interpolation in high-dimensional space, or intuition are kind of biased toward low dimension, and we have to be very careful what we say. So that was the main thing, and we have a bunch of turns out mathematicians that worked on these questions for many years, and there's a whole bunch of theorems about this that we survey in the paper.
Very interesting. Well, we'll dig more into that in a second. But folks like Gary Marcus make the case that deep learning models don't reason and only interpolate. Now, I know you disagree vehemently, but my intuition is that reasoning and extrapolation are somewhat synonymous. Is it by arguing that deep learning models extrapolate, are you kind of making the argument that they reason as well? Because that would make a strong case that deep learning models could scale to artificial general intelligence.
Okay, so no, the short answer is no. But there is there are important questions in there. First of all, what's our definition of reasoning? What is the process by which we elaborate models? And is there a qualitative difference between a models that merely performs curve fitting, as we normally know it, and a model that has a, let's say, to adopt a terminology that others have proposed, that models that establish sort of a causal model of the data you're observing, which can be the basis for reasoning and things like that, right? And the answer to this is probably no. There is a difference, of course, but is it an essential qualitative difference? I'm not entirely sure. And then there is the argument, if there is a qualitative difference, which I'm not sure about, would this qualitative difference be in the form of fundamentally different things from deep learning, things that are, like discrete symbolic reasoning or things of that type? And to that, my answer is clearly no. I do not believe that's the case. So I think reasoning is certainly, I always list in my talks, giving the ability to learning machines to reason is one of the main challenges of the next decade, or perhaps couple decades in AI. So I'm clearly aware of the fact that they don't do this very well at the moment. The big question, I think, is how do we get machines to reason in ways that are compatible with deep learning? Because most of the criticism that I've heard from Gary Marcus and several others towards deep learning is not a criticism towards deep learning. It's a criticism towards supervised learning. And I agree with them. Supervised learning sucks. I mean, it's very limited in the sense that you can train machines to do very specific tasks. And because they're trying to do very specific tasks, they're going to use all the biases that are in the data to do that task. And if you try to get outside of that task, they're not going to perform very well. That's a limitation of supervised learning. It has absolutely nothing to do with deep learning. So regardless of which learning techniques you're going to use, you're going to have that problem. It's a problem with supervised learning. So I take exception with the confusion between deep learning and supervised learning. Now, of course, today, most of supervised learning is deep learning, but it's a limitation of supervised learning. And as I have been, as you probably know, I've been a very strong advocate of self-supervised learning, sort of moving away from task-specific supervised learning towards, more kind of generic learning followed by specialization, using supervised or reinforcement learning. In that, I've kind of followed the path of Jeff Hinton, who's been basically, advocating for this for over 40 years now. For me, it's less time. I disagreed with him originally and changed my mind about 20 years ago. So that's the story, really.
It's awesome that you have the ability to change your mind and admit that this is a good thing. We run into so many people that are just, they don't want to change their mind no matter what. It's seen as a bad thing, which it isn't at all.
No, I mean, I think the essence of being a scientist is to be able to change your mind in the face of evidence. You cannot be a scientist if you have preconceived ideas. On the other hand, I've also been known to hold very tight to ideas that I thought were true in the face of considerable, differing opinion from my dear colleagues. So it also helps to have, deeply held convictions sometimes.
So to this notion of interpolation, I think, we've also, and you mentioned this, right? It depends on your definition. And we've also had a little bit of the sort of the feeling that people might be talking past one another when they, criticize, can it interpolate, can't it interpolate? And we've come up with this example of, I give a classifier a dog, and that dog is like the most doggy dog I've ever seen. Like it's like such a dog. It's more dog than any dog I had in the training data set. So clearly that dog is like outside of the training distribution, outside of the convex hull, in any space, like be that the original space, be that the latent space. It's like, but all that matters is that it's on the correct side of the classifying hyperplane. So that would not be contained on sort of in the convex hull. It would not be contained in the smallest ellipsoid, and so on. So do you think when people talk about interpolation, they might be talking about something maybe different? Because you can also make the example, if I take the convex hull of all the training data points and I take a point in the middle of it, the neural network is going to be pretty bad at it, right? That's going to be like a messy blur of pixels, and it's not going to be very, very good at it. So could you maybe make the strongest argument you could for people saying neural networks just interpolate, but what notion of interpolation would you substitute? Would it be like, oh, they just nearest neighbor classify, or they just, like, if you had to like give the best shot at sort of doing neural networks just do something, what would it be?
I wouldn't give any answer of this type, because the answer would very heavily depend on the architecture. So, for example, if most of the layers in a neural net, you can use weighted sums and sigmoids or weighted sums and ReLUs, right? And that effectively performs a classification, separating the input into kind of half, two halves, right, with the hyperplanes. But you could also use a Euclidean distance unit. So Euclidean distance unit computes the distance of the input vector to a weight vector, which is not a weight vector anymore, and then passes it through some sort of decreasing function like an exponential. And what that gives you is a Gaussian bump in input space, where the activity will be high if the input is close to the vector and low if it's not. When you have an attention layer, where you have a whole bunch of those kind of vector comparison, where the vectors are normalized, and then you do a softmax, you're basically doing sort of a multinomial version of this. And this is using transformers, right? And in all kinds of architectures these days. So those things that compare vectors with each other and only react if the two vectors are nearby, do a sort of, glorified nearest neighbor with some interpolation. By the way, most kernel-based methods do this, right? Kernel methods basically are one layer of such pairwise comparisons. Comparisons of the input with the training samples, and then you pass that through some function, some response function. So Gaussian SVMs, for example, are the perfect example of this. And then you take those scores and you compute a linear combination. That's glorified, interpolating nearest neighbor. To some extent, transformers do this as well. Transformers are the basic module of a transformer is basically an associative memory that compares the incoming vector to a bunch of keys, and then gives you an answer that is some linear combination of values, right? So that is a good idea. It learns fast. There used to be a whole series of models that are now forgotten in the 90s, called RBF networks. So an RBF network was basically a two-layer neural net, where the first layer was very much like an SVM. This was before SVMs, that again had radial basis functions responses, right? Comparing an input to vectors and passing it to an exponential or something like this. And then you would initialize the first layer. You could train it with backprop, but it would get stuck in local minima. So that wasn't a good idea. You had to initialize the first layer with something like k-means or mixture Gaussian or something like that. And then you could either just train the second layer or fine-tune the entire thing with backprop. And that worked pretty well. It was actually a fairly fast learner. They were kind of faster than neural nets. So for those things, the answer to your question is of one type. They're basically doing interpolation with kernels, and it's very much like a smooth version of nearest neighbors. But then for classical neural nets, where you have either a hyperbolic tangent nonlinearity or ReLU or something of that type, something with a kink in it, or two kinks, the answer is different. There, it's a whole cone of response that will produce a positive response versus not if you take a combination of units, right? what does it make sense to talk about interpolation in that kind of geometry? I'm not sure. I think people should just not use the word interpolation for that situation. But the fact that kind of things in a neural net, the response of a neural net actually are kind of have space, extend beyond the training points, perhaps has something to do with the fact that they do extrapolate in certain ways that may or may not be relevant for the problem, but they do extrapolate.
Well, so we talked some about the interpolation versus extrapolation versus what was in the paper, because the paper is somewhat a rigid definition. It's like there's this convex hull, and if you're inside, it's interpolation. If you're outside, it's extrapolation. And you talked about maybe we could use a ball, an ellipsoid instead, but there's kind of a key thing there, which is that it's going across all dimensions. So you're inside the convex hull. It's a necessary condition that on every single dimension, your sample data point falls within the range of the training data. We could kind of go the opposite extreme and say that you're interpolating if any dimension falls within the training domains, or rather you're extrapolating only if every single dimension falls outside the training range. And both of those are kind of these exponential extremes. And it would seem like the truth is maybe somewhere in between, like there's a subset of dimensions that might be salient for any particular data point. So why are we kind of using this very exponential extreme definition?
It was still exponential. Even if you can try to divide the set of dimensions into the ones that are useful and the ones that are just kind of nuisance parameters that are useless, but that are not relevant for the task at hand. But first of all, that task is very difficult. I mean, basically, the entire machine learning problem is exactly that: trying to figure out, what information in the input is relevant for the task, and what part is, should basically be considered as noise or nuisance parameters. So solving that problem is solving the machine learning problem, first of all. Second of all, what we show in the paper is that regardless, so what we did, the experiment we did, that Randall did, as a matter of fact, is, train ResNet 18 or 50 or whatever on ImageNet or CFAR or MNIST, and then take the output representation and see whether this sort of exponential growth of number of data points to stay within the interpolation regime still exists, and it still exists. It's just that the dimension now, instead of being the input dimension of the data, which may be very large, is the dimension of the embedding. But as soon as the dimension of the embedding is larger than 20 or so, the number of training samples you would need to get outside of to stay within the interpolation regime is already going to be very large. 2 to the 20 is a large number. So there's another experiment that shows that if your entire data set is contained within a linear subspace, so the ambient space may be of dimension 100, but the entire data set is within a linear subspace of dimension 4, then what matters is the dimension 4, not the dimension 100, right? So automatically, that convex hull process, what matters to it is not the dimension of the input space, is the dimension of the linear subspace that contains all the points.
Right, but I think what I'm saying though is that you can invert the definition so that whether or not you're extrapolating just becomes 1 minus whether or not you're interpolating, or vice versa, and so you can wind up with an equally extreme definition that concludes everything is interpolation. So I'm just wondering, it seems like there should be a balance, and this kind of gets to what you said earlier. Is there a more useful definition of interpolation versus extrapolation that could have some utility for machine learning?
I mean, it's not clear you would get much out of it. I give you a potential candidate, which is whether the points are contained in an ellipsoid that contains all the points. You could make it a sphere. A sphere would be, of course, bigger volume because the data doesn't necessarily have the same radius in all dimensions. But I think the result would be fairly similar for both. For both definitions, that in that case, things would be mostly interpolation. But that would be kind of a weird definition of interpolation, in the sense that it will rely on a false intuition about high-dimensional geometry. Okay, calling this this interpolation basically would mean that you have the completely wrong idea about how things behave in high dimension, right? About geometry in high dimension.
I'm trying to get some intuition about this because we spoke to Professor Bronstein and his friends, including Juan Brunner, and they're talking about geometric deep learning and their approach to defeating the curse of dimensionality is finding geometric priors to reduce the hypothesis space, which is quite interesting. But a lot of this is about our intuitions of interpolation, because if I take an autoencoder and I train it on MNIST and I start interpolating between the train or the test examples, it is learning this continuous geometric morphing, and that is what people's intuition is about interpolation. I know you would say that's extrapolation, right?
No, I wouldn't. No, I think it would be a type of interpolation, but it would be some sort of geodesic interpolation, interpolation on a manifold, right? I mean, so certainly if you have some idea about the structure of the data manifold, you can interpolate within that manifold without, making big mistakes. But then you're back to the original problem of machine learning. What is that manifold? How do you learn that manifold? I mean, that's one of the essential problems of machine learning. And learning the structure of a data manifold is a much more complex problem than learning a task of classifying objects on that manifold. For example, classifying points on that manifold. So there is this old adage by which I used to be a big fan of, and which is why I was disagreeing with Jeff Hinton about the usefulness of unsupervised learning, because if you have a task at hand for which you have data that you can use to train a supervised system, why would you go to the trouble of training pre-training a system in unsupervised mode, knowing that the unsupervised learning problem is considerably more complicated from every aspect you can think of, right? Certainly from the theoretical point of view. Vladimir Vapnik actually has kind of a similar opinion. One of the few things that he and I agree on, or agreed on at least, which is, why would you want to solve a more complex problem than you have to? But of course, that forgets the fact that you don't want to solve a single problem. You want to take advantage of multiple problems, and whatever data you have available at your disposal to prepare for learning a task. And we have access to considerably more unlabeled data than we have access to labeled data. And therefore, why not use unlabeled data in large quantity to pre-train very large neural nets so that we can fine-tune them for the tasks that we're interested in. So that's the whole idea of self-supervised learning. And of course, we all know that that kind of strategy has been unbelievably successful in natural language processing, with denoising autoencoder or masked autoencoder or BERT-style training of transformers, followed by a supervised phase. That success has not yet translated in the domain of vision, although I'm sort of predicting that it will happen very soon. But I mean, there's a lot of interesting avenues there and recent progress. And then there is the cake analogy, right? The fact that any sample in sort of a self-supervised context give you way more information than a supervised sample, the label from supervised learning, a fortiori reinforcement in the context of reinforcement.
Absolutely. We interviewed Ishan, so we've done a show on self-supervised learning. We're huge fans of self-supervised learning, and I know your vision is to get to these latent predictive models, to solve that problem.
That's something else I changed my mind on in the last 2 years. This may be outside the scope of this particular interview, but there's basically two major architectures, right, for self-supervised learning, particularly in the context of vision. And the main characteristic of both of them is it's the fact that it can handle multimodal prediction, right? So if you have a system, let's say you want to do video prediction or something like that, right? So you have a piece of a video clip, you want to predict the next video clip. Or you just want a machine that tells you whether a proposed video clip, continuation clip, is a good continuation of the previous one. You don't want it to predict, you just want it to tell you whether it's a good one. Okay, so you have two architectures. The first one is a latent variable predictive architecture that predicts the next video clip. And of course, you have to parameterize the prediction with a latent variable because there are multiple predictions that are plausible. Okay, so I used to be a big fan of that. And about 2 years ago, I changed my mind, maybe a year and a half. The other approach is something I played with in the early 90s, came up with some of the early models for this, and it's called a joint embedding architecture, where you have the first and the second video clip both going through a neural net. And then what you're doing is you're training the system so that the representation of the second video clip is easily predictable from the representation of the first one. Okay, so there you're not predicting pixels, you're predicting representations. But you still have a system that can tell you, here is a video clip and the second one, tell me if they are compatible, if one is a good continuation of the other. The main reason why I stayed away from those architectures, because I knew that you had to use, in the past, you had to use contrastive learning, right? You have to have pairs of things that are compatible as well as pairs of things that are incompatible. And in high dimension, there's just too many ways two things can be incompatible. And so that was kind of doomed to failure. And I played with this, back in, this used to be called Siamese networks, right? Had a paper in 1992, 1993 on doing signature verification using those techniques. Jeff Hinton had a slightly different method based on maximizing mutual information with his former student Sue Becker. But then in the last 2 years, we've had methods that are non-contrastive that allows us to train those joint embedding architectures. So I've become a big fan of them now. And it's because of algorithms like BYOL from our friends at DeepMind, like Barlow twins, whose idea came from Stéphane Denis, who was doing a postdoc with me at FAIR. He's now assistant professor at University of Aalto in Finland, and then more recently VicReg, which is a kind of a improvement, if you want, on Barlow twins that is also based on the same idea that Jeff Hinton and Sue Becker had of maximizing a measure of mutual information between the outputs of the two networks, but in kind of slightly different way. So I'm really excited about those things. And again, I change my mind. I change my mind all the time whenever a good idea, seems to be overcome by a better one.
So in this whole space of maybe interpolation, extrapolation, but also data manifolds and so on, what's your view on things like data augmentation, training and simulation, and domain adaptation and so on? Because it could be argued that these things kind of increase the convex hull of the training data. They sort of make the distribution broader, or is that just also out of question?
Not much. I think data augmentation does not increase the volume of the data point cloud, if you want, very much, because those augmentations are generally fairly local in dimensions that are already explored, right? So, I mean, it may increase it a little bit, but not significantly, I think. Obviously data augmentation is very useful, right? I mean, we've used this for MNIST, for decades. So it's not a new phenomenon either. There's a lot of ideas along those lines, right? So there's this idea of, it's the idea where you give two examples and you have two examples in your training set, and you actually do an interpolation in input space to generate a fake example that's in between the two, and you train it to produce the intermediate target between the two original examples.
Mix up. Yeah.
There is that. There is distillation. There is various techniques like this are basically implicitly kind of ways to fill in the space between samples, right, with other kind of fake samples or virtual samples, if you want. There was a paper by Patrice Simard and me and John Danker many years ago when we were all at Bell Labs on something called tangent prop. So the idea of tangent prop was kind of somewhat similar. The idea was you take a training sample and you're going to be able to distort that training sample in several ways. You could generate points by data augmentation, but the other thing you can do is just figure out the plane in which those augmentations live. Okay, and that plane is going to be a tangent plane to the data manifold. What you want is your for a given class, for example, right? So what you want is your your input-output function that the neural net learns to be invariant to those little distortions. And you can do this by just augmenting the data, or you can do this by explicitly having a regularization term that says the overall derivative of the function in the direction of the spanning vectors of that plane should be 0, or should be whatever it is that you want it to be. But 0 is a good target for this. So that's called tangent prop, and you can think of it as a regularizer that says, I don't just want my input-output function to have this value at this point. I also want its derivative to be 0 when I change the input in those directions. That's another indirect way of doing data augmentation without doing data augmentation, essentially. I think there's a lot of those ideas that are very useful, certainly.
So I think there seems to be like a spectrum. Coming back to this interpolation, extrapolation, you said yourself you don't believe neural networks can do something like discrete abstractive reasoning and so on.
No, I didn't say that.
Or yeah,
I said we need to do work for them to be able to do that, but I have no doubt that eventually they will. I mean, there's a lot of work in this area already, and I'll give you some more specific examples if you want.
I mean, that's actually kind of the nature of my question. Where do you think, there is this spectrum of what people think neural networks are doing now or will be able to do later. Where do you think the actual biggest disagreement between sort of the community right now lies, and what can we do to, like, what experiments, what evidence can we gather to solve these disagreements?
Right. So I think we shouldn't talk too much about neural networks, because people have kind of a really relatively narrow picture of what a neural network is, right? It's, a bunch of layers of neurons that perform, weighted sums and pass a result through a nonlinear function. And there's a fixed number of layers, maybe they can be recurrent, but, and you produce an output. That's a very restricted view of what deep learning systems can do. So let me take an example of what reasoning might mean. Reasoning might be seen, at least one particular type of reasoning might be seen as a minimization of an energy function, not with respect to parameters in a neural net, but with respect to latent variables. And a lot of systems that are in use today do that. So a lot of speech recognition systems, for example, have a decoder on the output, which, essentially given a list of scores for what a particular segment of speech could be in terms of what sound it could be or what syllable or whatever. The decoder basically figures out what is the best interpretation of that sequence of sound that makes it a legal sentence in the dictionary. Techniques like this have been used for 25 years now in the context of speech recognition and handwriting recognition, even before neural nets were used for those things. So, back in the old days of hidden Markov models, and those techniques have been, really developed. Now, if you think about what those techniques do, first of all the operations that are done in those systems are differentiable. You can backpropagate gradient through an operation that will figure out the shortest path in a graph using dynamic programming. The first paper on this was in 1991 by my friend Léon Bottou and Xavier Driancourt. This is not recent stuff, and they were trying to do speech recognition. You can backpropagate gradient through a lot of different modules. What those things do is that they infer a latent variable by basically doing energy minimization. Finding the shortest path in a graph is a form of energy minimization. And so you can have, in a deep learning system, you can have a module that has latent variable. And what this module will do is figure out a value of the latent variable that minimizes some energy function. It could be a prediction error. It could be something else. It could be, there could be regularizers in it, etc. But it basically performs a minimization. And that type of operation basically can be used to, like, you can formulate most types of reasoning in that form. Now, it's not necessarily in a continuous differentiable space, but almost all reasoning, even in classical AI, can be formulated in terms of optimizing some sort of function. Like, you won't do a SAT problem, right? You have a collection of Boolean formula, you want to find a combination of variables that satisfy this formula. It's an optimization problem. It's combinatorial optimization, but it's an optimization problem. You want to do planning. So planning is the best example. So you can do a planning where the thing you're controlling as discrete actions and discrete states, and you have to use dynamic programming. You can backpropagate gradient through a system that does that. But more classical planning is in continuous space. So planning the trajectory of an arm for a robot, planning the trajectory of a rocket. What you have is a differentiable model, dynamical model of what is the state of the system you're trying to control at time t+1 as a function of the state at time t, and as a function of the action you take, and perhaps as a function of some random variable you can't measure, from the environment or something like that, to make it non-deterministic. Now you can unroll that model. So start with time equals 0, and then make a hypothesis about a sequence of action, and then apply your predictive model of the next state of the system. And then at the end, you can measure some cost function. Is my rocket, docking with the space station, or is far away? And how much fuel have I consumed? Or, whatever, right? Or have I, reached the goal of the arm, avoiding all the obstacles, right? So what you can do now is an inference process, which consists in figuring out what is the sequence of action I should take to minimize this cost function according to my dynamical model. And you can do this by gradient descent. And basically, that's called the Kelly-Bryson algorithm, in optimal control. That goes back to 1962. And it consists in basically doing backprop through time. It's as simple as that, right? So you do backprop through time. So in effect, optimal control theorists invented backprop back in the early 60s, but nobody realized you could use this for machine learning until the mid-80s, essentially, or the late 70s.
Just to jump in there, because there's a little caveat there, which is that you can do that at backprop if you have a fixed number of steps. Like what backprop can't handle is the case where I want some expandable number of steps. We have no algorithms that can currently optimize, for example, neural networks with a variable number of layers. Like we just can't train those, right?
No, it's not true. It's not true. That's what recurrent nets are. You can have a varying number of iterations in your recurrent net. And what I'm describing here is an unfolded recurrent net. It's the same model that you apply at every time step, right? So it's very much like a recurrent net. And you can very well have an unknown number of steps. You don't know a priori how long it's going to take for your rocket to get to the space station, right? So you may have kind of a large potential number of steps, and you can have a cost function which will count how much time it's going to take to get there. And this will be part of the optimization, for example. And this is classic optimal control. I'm not telling you anything that I came up with. This is, from at least the 60s and 70s. That
variable number of layers has to be done in kind of a classic iterative, try out the variable number of layers and see what the backprop comes up with, or you start with a very large number of layers and then let backprop try and find. But still, it's what I'm saying is there is fundamentally two different kinds of computation that are at play here. One is like the finite fixed thing, and then you do some differentiable optimization on it. Another kind of computation is this discrete symbolic that has like an expandable memory and an unbounded amount of time to sit there kind of computing on things.
Okay, I put a stop right there. What I'm describing has nothing to do with symbolic, discrete, or anything. Okay?
I understand that. I understand that.
But you seem to be equating variable number with discrete symbolic. This is two different things.
Okay, let me pose it in this form, which is that I can very easily write down a symbolic program that can output the arbitrary digit of pi, like the nth digit of pi. Nobody can train a neural network that can do that. So what's the difference between these two types of computation, and where in the future might we go with neural networks, or by augmenting neural networks, whether it's differentiable Turing machines or whatever, or neural Turing machines to try and bridge that gap in capability?
Okay, before we bridge that gap, the algorithm to compute the digits of pi, there's only a tiny number of humans, only in the last few centuries, that have figured this one out. I'm interested in how is it that a cat can plan to jump on a table and not fall, or even open a door, or do things like that, right? Once we figure this one out, maybe we can think about kind of more complex stuff like designing algorithms that involve complex mathematical concepts. But I think we're way, we're not there. We're not there, right? I mean, we're faced with much more fundamental issues of like how do we learn predictive models of the world by observing it, and things of that type, which
that's fair.
are much more basic, that most animals can do, and justify it's sometimes
that's fair.
down the line.
Yeah.
So, because you're talking about model predictive control, and is it possible that there are different shapes of problem? So, for example, some problems are interpolative and are solvable using, differentiable models. Do you think there exists problems that are quite discrete in nature, and a different type of approach would be required?
Of course, yeah. I mean, there is certainly a lot of situations where the mapping from action to result is very kind of discontinuous, if you want, right? There's qualitatively different, So there are many situations where it's somewhat continuous, and situations where you change your action a little bit and it results in a completely different outcome. And so the big question, I think, is how you handle that kind of uncertainty in the search. And you can think of sort of two extremes. So at one extreme in the continuous case is the case where you're planning the trajectory of a rocket, or that's pretty continuous and differentiable and everything you want. And you don't even need to learn the model. You basically write it down, right? But there are situations there where, you're flying a drone or something where you might need to learn the model because there's so many kind of nonlinear effects that, it's probably better to learn it. And people are working on this. Same for like walking robots and stuff like that. Then there are things that are a little intermediate where there are sort of hard constraints on what you can do. So you want, to grab an object with a robot arm, but there is obstacles in between and you don't want to bump into them and things like this. So people tend to put like penalty functions to make this sort of more continuous, but there's sort of qualitative difference between using your left arm or your right arm, for example, or going, scratching your left ear with your left hand, or with your right ear, going to the back of your head, right? Those are qualitatively different solutions. And then all the way to the other side, there is intrinsically discrete problems with, that may be fully observable with some uncertainty, like chess and Go playing. Okay, and those we can handle to some extent because the number of actions is finite. It grows exponentially, but it's finite, and so using kind of ways to direct the search, despite the fact that the search space is exponential. Using neural nets as basically evaluation functions to direct the search in the right way, and doing Monte Carlo tree search and blah 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 will work, okay, with sufficiently many trials. In the completely deterministic, fully observable, differentiable case, that's classical model predictive control. That's fine. Then there is the stuff that we really don't know how to do, and it's twofold. One is the model is not given to us by equations derived from first principles, right? So the stuff we're trying to do, is in the real world, and it's got complicated dynamics that we can't just model from first principle. So we have to learn the model. That's the first issue. Second issue, the model lives in the world, and the world is not completely predictable. It may be deterministic, but you don't have full observation, so you cannot predict exactly what's going to happen in the world, because the world is being the world, or as a consequence of your actions. So how do you deal with uncertainty? And for that, you need predictive models that can represent uncertainty. And we're back to the issue I was telling you about earlier. Do you need latent variable models or joint embedding architectures, right? That's and I've changed my mind about this, as I told you. So then there is the third obstacle, which is the problem we're trying to solve of the sort of continuous differentiable nature, or of the kind of completely discrete, qualitatively discrete, depending on what action you take, nature. And I think most problems are some combination of the two. So, you're trying to build a box out of wood or something like that, right? You can make the box bigger or smaller. You can hit the nail in this way or that way, and that may be sort of continuous and differentiable. But then there is, you put glue or screws or nails. Do you or use kind of more classical carpentry or whatever? And those are kind of discrete choices. What type of wood are you using? Things like that. So I think the human mind is able to deal with all of those situations, have know to use differentiable continuous stuff when they have to, and use the sort of discrete exploration when we have to as well. But we have to realize that humans are really, really bad at the discrete exploration stuff. We totally suck at it. If we didn't, then we would be better than computers at playing chess and Go, but we're not. We're actually really, really bad. So
that's fascinating. So you seem to be saying in a way that you are a fan of hybrid models and something like AlphaGo, for example. I mean that's basically there's an interpolative space which guides a discrete search. Let's say it like that. Do you think is that a good thing, or do you think that's so you like that kind of model?
Okay, there's something very interesting about in the context of reinforcement learning about this, which is actor-critic models, right? And you could think of all of the stuff that actually works in reinforcement learning. I mean, they don't work in the real world, right? But they work in games and stuff and simulated environment. They very often use actor-critic type architectures. And the idea of a critic, goes back to early papers by Sutton and Bartow. And the basic idea of a critic is to have a differentiable approximation of your value function, right? So you train a small neural net essentially to compute, to estimate, to predict the value function from your state. And the reason you need this is now you can propagate gradient to it, right? So that's kind of the first step into sort of making the world differentiable. You're just making the value function differentiable. Now, inside of the world, there's two parts, in my opinion. And this is the source of the idea behind model-based reinforcement learning, is that you have the model, you have the world, right? The world is going from state to state because it wants to, or because you're taking an action. And then there is a value function, or a cost function. I prefer to talk in terms of cost function, that takes the state of the world and gives you kind of estimate of that cost, right? Or gives you the cost. Now, the world itself and the value function that takes the state of the world and gives you pain or pleasure, right, is unknown. But what you can do is build a differentiable model of that, right? So a differentiable model of that is what NPC is all about. You build a model of the world that predicts the new state of the world as a function of the previous state. It doesn't have to be a complete state. It has to be a state that's complete enough to contain the relevant information about the world, related to your task, right? And then you have a differentiable function that you learn that learns to predict the reward or the cost from your estimate of the state of the world. So what you have now is, a neural net inside your agent that basically can simulate the world and simulate the cost that is going to result from the state of the world in a differentiable way. So now you can use gradient descent or gradient-based methods for two things. One, for inferring a sequence of action that will minimize a particular cost. Okay, there's no learning there. Two, to learn a policy that will learn to produce the right action given the state without having to do model predictive control, without having to do this inference by energy minimization, if you want. And that, in my opinion, explains the process that we observe in humans, by which when you learn a new task, you go from the Daniel Kahneman system 2 to Daniel Kahneman system 1, right? So you learn to drive, you're learning to drive, you're using, of course, your entire model of the world that you've learned in the last 18 years, if you are 18, to predict that, when you turn the wheel of the car to the right, the car will go to the right, and if there's a cliff next to you, the car is going to fall off the cliff and, you're going to die, right? You don't have to try this to know that this is going to happen. You can rely on your internal model to, avoid yourself a lot of pain, right? And so, but you pay attention to the situation. You pay a lot of attention to the situation. You're completely deliberate about it. You imagine all kinds of scenarios, and you drive slowly, so you leave yourself enough time to actually do this kind of reasoning. And then after maybe 20, 50 hours of practice, it becomes subconscious and automatic. That's even true for chess players. So that's an interesting thing about chess, right? I played once. I'm a terrible chess player, by the way, and I played once a simultaneous game against a grandmaster. So he was playing against like 50 other people, and so I had plenty of time to think about my move, right? Because he had to kind of play with the 49 other players before getting to me, and so I wait for him to come and I make one move, and then in 1 second, no, first of all he does as if I played something stupid, which I did, and he moves within 1 second. He doesn't have to think about it, right? It's completely subconscious to him. It's just pattern recognition, right? He's got this, ConvNet predicting the next move, completely instinctively. He doesn't have to think because I'm not good enough for him to really kind of cause his system to kick in. And of course, he beat me in 10 plies, right? I mean, as I told you, I'm terrible. I learned to drive a long time ago, but as it turned out, very recently, I went to drive a sports car on a raceway, and again, the first few times you were very deliberate about it. They explain you a few things, and then you basically have to integrate all of that by yourself. And over the course of a day, you get better and better, like much better, just by basically compiling what at first is deliberate into something that becomes automatic and subconscious.
Indeed, and also abstractly reusing knowledge that you've gleaned elsewhere and applying it in a new situation. But anyway, Professor Yann LeCun, thank you so much for joining us today. It's been an absolute honor.
It's been a pleasure. You guys are doing great work, so keep going.
Thank you for being a fan too. Thank you so much for watching some episodes.
Thank you so much.
Thanks.
Wonderful.
Randall, introduce yourself.
Okay, so I joined FAIR, or should I say Meta AI Research, I guess, last June for a postdoc position. I was doing my PhD at Rice University under the supervision of Professor Richard Barenyuk. And during my PhD, I focused on basically trying to understand deep networks from a geometrical point of view through spline theory. And now I'm trying to, let's say, expand my horizons and do more diversified research topics with Yann LeCun. And for this paper, basically the main goal was to try to understand through a lot of empirical experiments, what do we understand by interpolation? Does it occur in practice? And does it make sense to use interpolation as we know it as, let's say, a measure of generalization performance for current networks? And the main point is really to say that the current definition of interpolation, which uses this convex hull, might be too rigid to really provide any meaningful intuition. And so we either need to adapt this definition or just entirely think about this in a different angle. But yeah, the current definition is not good enough for the current data regimes that we are in right now. I don't know if it's precise enough.
Perfect.
No, it's wonderful.
Cool. Well, sorry, need to get into the mood again. Yeah. Hi, Randall. It's really cool to have you here. We've enjoyed reading the paper. It's quite a short and concise paper,
yes.
I have to say, and the experiments are quite. I find them to be really on point, especially where you look at the latent space experiments, because a lot of people would say, of course we're not interpolating in data space, we're interpolating in the latent space.
Yes.
Yet even in the latent space, and we've talked a little bit about the notion of interpolation and extrapolation. Is it fair to say that the paper is just sort of a negative argument? Is it fair to say that the main point of the paper is arguing, look, interpolation is the wrong concept you're looking for when you criticize these models?
Yes, I don't think it's negative per se. It's more, let's say, a call to change the definition for the current usage of machine learning models, because now we are not in low dimension regimes anymore. And so using those concepts that have been defined 50 years ago when we were looking at univariate models does not really make sense. So I think the intuition behind what we try to mean by interpolation is right. We should not change that. We should change the mathematical definition of it. And yeah, like you say, people could argue, yes, but you have interpolation in the latent space and so on. But we showed that even in a classifier setting, it does not happen. And you can also show that in a generative network setting, it will not happen again, all because of the dimensionality. So it's really about going to the high dimensional setting, then things start to break, and we have to adapt to that, basically.
And we've already asked Yann this question, but if you had to give your best shot at making the argument that these people want to make when they say, oh, it's just interpolating,
Mm-hmm.
if you had to give your best shot at making that argument successfully, what would you change? How would you change the notion of interpolation, or what argument would you make for those people?
So I think what most people try to say is they try first to conceptualize the data that they have. So for example, you have an apple, right? You have different colors. And if you think of this color as being your latent space, then you can say, okay, between green and red, you have a new color, but it's in between the two, you are in an interpolation regime, right? So all of this point of view is from a generative perspective. And this is because you only think of a few factors of variations like this, and then you think, okay, everything should be in interpolation regime. But even with that definition, if you start having a lot of factors of variation, then the curse of dimensionality will kick again, and you will never be in interpolation regime, even in a generative setting. So for them, the best argument will be, if I don't consider the real data set, but a very low dimensional approximation, very rough, which can be explained only with a very few factors of variation, and I can somehow linearize those factors in my latent space, then I will have more chance at being in an interpolation regime. So we'll have to have a sort of lossy compression of your data, if you will, and then you can try to reach there with more chances.
So I think you just steel-manned the argument for interpolation. So I think that's precisely what folks do argue is happening in a deep neural network. Do you not believe that?
Mm-hmm. Well, as soon as you have high dimensionality settings, then it does not happen almost surely. And I mean, you could argue, so for example, let's say you take a GAN or any big generative network, right? In the latent space, you have hundreds of dimensions, and you sample those guys from a Gaussian distribution. So even if you were saying, okay, your training set is sampled from a generative model, and your test set is sampled from the same generative model, and in that latent space you have interpolation, well, it's wrong from the beginning, because in that latent space alone, you will never have a Gaussian sample that lies in an interpolation regime as soon as the dimensionality is greater than, let's say, 15 or 20. So it does not happen because of the dimensionality, unless you have very degenerate things. Of course, if your generative network just spits out a constant, then in pixel space, you will have interpolation. But this is degenerate by definition. So
I'd like to pick up on that, if you don't mind. Yeah, so what I want to pick up on is, again, all of this hinges on definition 1, which is in the paper,
yes,
which is membership within this convex hull. And
yes,
there's a sense in which that's an extremely rigid definition of interpolation, right? And
yes.
And I think I heard you earlier say that what we need to do is redefine what we mean by interpolation in higher dimension, because the intuition of interpolation is still correct, but we need to redefine what we mean by interpolation.
Yes.
So if you took a shot at redefining interpolation, how would you define it? What do you think is a better definition of interpolation?
So I think it's very task dependent. So let's say you want to look at a task which is pure object classification. In that case, I think going back to what we were saying earlier on first trying to compress somehow your data so that you can explain it with as little factors of variation as possible. And then you can use the current definition just on a compression of your data. Then it could make sense because you don't really mind about the finicky details of your objects if you just want to differentiate between different classes of objects. But in another setting where you might be trying, to denoise samples or things like that, then you might want to have a very more specific definition based on what you try to denoise in your data, and so on. So I don't think there will be a general definition that works across the board. It will be really dependent on the type of task you are looking downstream. It's really the key.
Let me throw something out there, because I've been thinking about this, and I tried to ask Professor LeCun about this, but I didn't communicate it clearly, which is that for something to be in the convex hull, so in dimensions, for something to be within, a convex hull, it's a necessary condition that on every single dimension, the sample data point lies within the range that was sampled. So that's a necessary but not sufficient condition, because that's sort of, the convex hull is actually even smaller than that space, but it's necessary that it be within that bounding, that axis aligned bounding box. It has to be inside there. On every dimension. Okay. And so what if I were to invert this and say that, well, instead I'm going to define extrapolation as on every single dimension, it has to be outside the sample range. So in other words, a point has to be outside the axis aligned bounding box. That would actually come to the complete inverse conclusion, because then exponentially so, all machine learning would be interpolation, because it's very, very unlikely that you're outside every single dimension. So I'm thinking somewhere in between there, like there's almost like a fractional concept of interpolation versus extrapolation, where we can say it's almost like, on average, how many of the dimensions do you hit inside the sample point? So maybe I'm inside 20% of the dimensions on average. Could that be like a route to any type of improved definition?
So that's actually a very good point. So basically what you are saying is, instead looking at, let's say, the closest enclosing hypercube, and then you say, okay, if you are in that hypercube or not, you are in interpolation or extrapolation regime. And that's actually something we are looking at right now, which is not the smallest hypercube, but the smallest ellipsoid that encloses your data. And it's somehow in between the convex hull and the hypercube that you mentioned. So for sure, there is some ways in between those two extremes where you will have a meaningful interpolation and extrapolation regime that does not collapse all one way or the other way. So this is for sure one interesting route. And this could potentially be, let's say, task agnostic. But then again, would it be precise enough to really quantify generalization performances per se? I don't know yet. But yeah, that's something we are looking into right now.
Yeah, and the reason that we kind of came to that thought process is because there is an intuition that machine learning is kind of very good at taking all these dimensions that we sample and saying, it's really only a subset of those dimensions that matter, at least in some transform way. Like for example, suppose I was doing, suppose I only had 16 dimensions of ambient space. And everybody agreed, given the amount of data we have, we are interpolating. Like almost all the time, we're in this rigid definition of a convex hull. And then somebody comes along and says, oh, by the way, we upgraded all our sensors now, and we added 240, dimensions. And if all those dimensions happen to not be useful for the problem that we're trying to solve, or classification problem or whatever, it would be weird to say now we're all of a sudden extrapolating, because if the neural network is doing what it should be doing, it will ignore all those irrelevant definitions and continue just calculating exactly what it was calculating, before. Is that right?
Yeah, that's a very good point. But I think for this to actually work, you need to assume that you have enough actual samples, so that when you train, your network understands that basically those dimensions are pure noise. It does not need it to solve the task at hand, and it disregards it. So you have somehow a regularization term that kicks in, and it does not try to use them to minimize the training loss. But I think in practice, that's not really what we see. If you take image task classifications, even especially now with self-supervised learning methods, we see that actually most of the information that we could think is irrelevant for the task is actually kept because it can, of course, help in reducing the training loss. So I think
that's a very interesting point.
For what you said to work, you really need to be sure that either you have the perfect regularizer or you have the perfect model and regime of training samples and so on. But in a general setting, I think it will be tricky to claim it like this.
That's a very interesting point. So you're saying when you add these extra dimensions, even to learn to ignore them, you have to have lots of data.
Yes, or regularization or some mechanisms that, exactly.
Yeah, very interesting.
That's one thing, that's one reason why, let's say, ad hoc parameterization by hand is sometimes useful, because if you know a priori which things are useless for your task, you can by hand remove them from the data that you feed to your DeepNet or whatever model. And then doing this, you will improve generalization. So that's why in some cases, it's still useful to do those, let's say, pre-processing steps.
Right. Could you give me a bit of intuition here? So we've been listening to quite a few folks that make the argument about the interpolative nature of deep learning. And you could argue that any kind of processing in machine learning, not just feature transformations, but even things like regularization and domain randomization, that they're all ways of making the problem more interpolative, and it would be appropriate for an interpolative problem. So I'm thinking to myself, I mean, in this example, you take pictures of clock faces, and it's not interpolative in the ambient space. You perform some kind of feature transformation. There exists some nonlinear transformation that transforms it into an interpolative space. That's what these people say. But I'm wondering, you know, I'm interested in the curse of dimensionality. You know, why does deep learning work at all? And I've spoken to folks that talk about creating various priors to combat the curse of dimensionality. But why do you think that deep learning works at all in these high dimensional spaces?
Well, so first, I might say something a bit, let's say, speculative, or I don't know, not agreed upon by everyone, but I don't think
we love it. Please do.
Exactly. I don't think you can state so generally that deep learning works, right? You need the right architecture, you need the right loss function, you need like everything right for it to work. And that's why it works now, because we spend, I don't know, much amount of money and manpower to get to where we are now. But if you just take a plain MLP, you apply it on ImageNet, I don't think you will say it's working, right? So I think right now it's working. I mean, what we have is working because we basically by hand did all the cross-validation such that the network that we are using is regularized enough to only learn the necessary or meaningful information, or at least as best as we can to provide good generalization performances. So yeah, it's a bit too general of a statement to say that deep learning works out of the box for everything. In fact,
I love that point. Yeah.
Yes. Many, if you go into not just image classification, but let's say audio classification and some maybe trickier data set where I don't have a lot of samples, then everything starts to break quite rapidly, right? You have always people trying to go into the medical field as well. But since it's very hard to generalize between patients, between recording devices and so on, things get very, very messy and everything is ad hoc and optimization, basically. So yeah, I don't think we're at this point yet where you can say, right, that's it, deep learning works.
Yeah, can I jump in real quickly here, Tim? Because what I want to say is, brilliant point. I mean, and when you think about it, let's take Professor LeCun, you know, one of his great invention, right? The CNN, convolutional neural network, that was discovered by a human being, like a machine. No neural network learned to do convolution. LeCun taught machines how to do convolution. And so we oftentimes discount this and say, look how great machine learning works. We discount all the human engineering that has gone into actually making machine learning work through specific architectures.
Yes, exactly. Yeah, that's basically we are guiding where to go. And then, of course, once we guide enough, the machine knows what to do. I mean, this is not a reduction of what we can do with deep learning, right? But it's just saying that a general statement of out-of-the-box deep learning works even in a new task that we've never tried before is an overstatement.
But I still want to linger on this point of why you said, or here's just a random projection of the data, and then here's a ResNet projection, here's a trained ResNet projection. And what I took from that is, irrespective, it's all in an extrapolative regime. And, there was a guy who posted an article who is disparagingly saying that neural networks are just interpolators, analogous to a Taylor series approximation within a small part of the domain of a function, and it goes haywire outside of the domain. And, there are a lot of people that would make that case, that neural networks cannot extrapolate outside of the training range, but they do seem to work remarkably well given the curse of dimensionality. So why is that exactly?
So let's say for simplification that you have a binary classification problem. So once you go into your latent space, or if you just do linear classification, if you stay in your ambient space, basically you say you have class 0 or 1 based on which side of an hyperplane you lie in. Now, if you are on the good side, you can go to the infinity, right? You can go to extrapolation regime as far as you want from the training set. As long as you are in the correct side of that hyperplane, you will have good generalization performance. So it's not exactly correlated. The only thing you need somehow is to have the orientation of the axis where you will extrapolate to be somewhat aligned in the orthogonal space of that hyperplane. Once you have that, then you will generalize, even though you can be in extrapolation regime in ambient or feature space. So that's one thing that is maybe proper to linear classification. If you were doing maybe some other type of classifier on top of it, it might change. But yeah, given the current settings, I don't think people should expect bad performance because you are not in an interpolation regime. This is quite of a shortcut, maybe that it's guided by our intuition, right? We think it's much easier to classify something if it's in an interpolation regime. But if you just look at the plain linear classifier, that's not the case.
Well, so just to steelman a bit what what say others on the interpolation side, again, that's only if you're buying into a very rigid definition of interpolation, which, the way the paper defines it is in a linear way. I mean, it's defining interpolation by this linear convex hull. And of course, neural networks, for example, are highly nonlinear systems. And what you just said, sort of which side of a separating hyperplane you're on, that itself is a nonlinear function. And so I think the point you made early on was very good, which is we have this intuition of what interpolation is. We haven't yet got a good definition for interpolation in multi or high dimensionality nonlinear cases. But obviously the linear definition doesn't really apply.
Yeah, exactly. Yeah. It's really because, it's linear, but again, you can consider your data as being non-linearly transformed. The problem is still that if you have high dimensionality, then to be within a convex hull becomes exponentially hard using the convex hull of the training set. If you define something else, like you said before, the hypercube, it could be the opposite. It's always in interpolation regime. And the key is basically to find a meaningful set such that you don't go all the way in one direction or the other. And because I think the main point also is that this should give intuition into the generalization performance of a model, right? Because if you can detect, a sample is in an extrapolation regime, but your model still performs very good on it, I don't know if it has really a lot of practical use. So what would be good as well is to have the basically generalization performance of a model correlate with your definition of extrapolation. And that's really what we are trying to get. And that's why I was saying that probably you might have a task-dependent definition, because that might be where you get the best precise definition to reach that.
I was wondering to what extent, if any of this invalidates the so-called manifold hypothesis. So I think when most people speak of interpolation in deep learning, their intuition is something along the lines of, well, the model learns some manifold in the latent space, and interpolation means I'm just kind of like traversing, the geodesic on that manifold. And when you visualize the results on an autoencoder or something, you can see this kind of continuous geometric morphing of, let's say, one image into another image. And that manifold, I think you said in your paper that the actual data manifold, it's not possible to approximate that well, but it's doing something interesting.
Yeah.
And a prediction on that manifold in the intermediate space, it's not massively deranged, is it? It's still doing something very useful statistically.
Yes, totally. So I think it does not at all contradict it. And in fact, think of a very, very simple example where you say your data is a linear manifold of dimension 100, let's say, which is a relatively meaningful number of dimensions, even for images. But now suppose it's completely linear. Well, even in that case, it will be hard to be in interpolation regime, just because you have 100 dimensions, and picking a new sample that lies in the convexer of your training set is exponentially hard. So you can have a manifold for your data. It can even be linear, so the simplest manifold you wish for. The only problem is the dimensionality of that manifold. Now, that being said, again, it does not mean that you cannot do basically moving on the geodesic of your manifold, or you cannot do some sort of interpolation, because that's what happens in most of the current state-of-the-art generative networks, right? It's just that you don't need to be in interpolation regime to have a correct generation process, basically. And that's, again, one thing that is very important. And you mentioned you have those examples. That's true that the interpolation is extremely nice, but again, it does not say that the points you start with and the point you end up with are in interpolation regime of your training set. So I think it's two different things to be able to interpolate or move on your manifold and being in the interpolation regime from your training set.
So what's intriguing me about, and I want to clarify something earlier, which is that though a hyperplane is a linear construct, the function that says you're on one side or the other of a hyperplane is a nonlinear function. And so and in that case, it's a digital function. You're either on this side or that side. It's 0 or 1. And what's kind of interesting is you gave that as an explanation for why machine learning works at all, which is that for data sets that we care about, or problem spaces that we care about, it seems to often be the case that we can do enough sequences of linear and nonlinear transformations to arrange the data such that it falls on one side or another of a separating plane. So in a sense, it seems like real world data is often separable if you do enough transformations on it. And since that separability is a very digital concept, is there anything interesting in that? Any intuition?
Yes. So for this, you still have to be careful, right? Because if you go in high dimensional spaces, you can basically separate everything very easily. But your generalization performance might be bad. So basically what you want is really to have, let's say, a good ratio of how much you expand dimension, how much you nonlinearly transform your data, to then reach a good generalization performance. Because otherwise you can just fall back into a kernel regime, let's say, and you expand so much your space that sure, you can separate everything on your training set, but then the generalization is going to be very poor. So, and that's one strength of deep networks, right? Is that you have so much of those nonlinear transformation that you can somehow not expand the dimension of your space too much, or even contract it, and still have a separating hyperplane in the end, where generalization is much higher than in other class of models. So I think the key is really to have those meaningful nonlinear transformations such that you don't have to increase your space too much. You just shape it around, if you will. But yeah, that's and what you said earlier is exactly true. If you think of which side you are in, basically you are binarizing your data, right? And if you have good classification, it means all the classes are assigned to the same labels, which is 1 or 0. And if you think of it still in interpolation regime, then suddenly you are in interpolation regime, right? You are a 1, the new sample is a 1 after binarization, and you become interpolation regime, and you have a good performance. But this comes after this compression step, if you will, or discretization step. And that might be another direction to explore as well. If you start to quantize things or to compress things, as we were saying a bit at the beginning, then you can reach basically interpolation much more easily as well.
I had a couple of questions. So again, in table one, your paper's making the argument that everything is extrapolation given this convex notion in high dimensional space. But if we zoom in a little bit though, so you were using a pre-trained ResNet classifier pre-trained on ImageNet, and how do all of these things change the structure of the latent space in a meaningful way? And the embedding space is also highly distributed, and we were wondering, can you give us some intuition here? So is the information likely to be quite evenly distributed over the latent, or do you think it's actually quite bunched up and sparsely encoded in few of the features?
So I think this will depend on which training setting you use, right? So for example, if you start using dropout and things like that, you will try to have a more evenly distribution of your information to have a more stable loss when you drop those units. So I don't think you have a general answer for that. It will depend on the type of regularization you have, how training is done, etc. But you have to keep in mind that what you try to do with gradient descent is just minimize your loss, right? But then with cross-entropy loss, let's say, your gradient starts to vanish as you become really good and you stop learning at where you are, basically. So given that, depending on your initialization, you will still try to make the best of what you get. And even if it means learning redundant dimensions, if this can reduce your loss further at a more rapid rate, that's what you will do. Right. So if you don't impose any regularization or anything, there is no clear reason to assume that everything is well organized and so on. And that's what we see even in generative networks. You have to start putting so much regularization to try to have disentanglement and to try to make sense of those latent spaces, because otherwise you just try to learn what minimizes your loss with the most short-term view of your loss landscape. So basically, that could be built if you have some specific regularizer, but otherwise it will not occur naturally. Of course, if again, if you wanted to only retain the minimal information to solve the task at n, then you will see much more interpolation regime in that latent space. If you think of MNIST, for example, you would disregard the translation of your digit, the rotation of the digit, all those things. All those things will be disregarded when you reach the latent space, and then you will basically be in interpolation regime most of the time. But since you keep as much information as possible to try to minimize your loss as best as you can, then you basically occupy as much as you can. Unless, again, you have some degeneracies because of the ReLU or architecture tricks. For example, if you have a bottleneck layer, right, you will limit the dimensionality of the manifold you span in the latent space. So you can have all those parameters that can play a big role. So it will be in the general setting, I don't think you could assume anything.
And I think there's also a relationship too between the dimensionality of the latent space and, let's say, some intrinsic dimensionality of the problem. So if the intrinsic dimensionality of the problem only takes 5 dimensions to solve, and yet I give a latent space of 256 dimensions, I think what I hear you saying is that, of course, gradient descent's going to make some use of those other, 251 dimensions, but they're going to have like maybe a very minuscule or diminishing effect on the latent space. Whereas on the other hand, if I then took that same network and increased the complexity of the problem, we could end up with, for example, it sparsifying for any particular class. So if we're doing some multi-class problem, we may find that it sort of arranges, these seven dimensions to solve the dog versus hot dog problem, and these 12 dimensions to dissolve the car versus motorcycle problem. It might be forced to make more compact use of that latent information space per class. Is that fair?
Yeah, so that's a very good point. So first, on the first thing that you said, one thing to keep in mind, so let's say your data is even a linear manifold of dimension 1, and then you go through a deep net, and then somehow it's already linearly separable. Then you only need to learn the identity mapping with your deep net to solve the task. But if you start from a random initialization, it's extremely hard to do that, right? That's why people came up with ResNet and all those things. So already from this point of view, it means that almost surely your linear one-dimensional manifold will become highly nonlinear, still one-dimensional, but very highly nonlinear in the latent space of your classifier. And as we showed in the figure 1 of the paper, even if the intrinsic dimension is 1, if you are highly nonlinear in your space, then you will basically never be in an interpolation regime. So you have those sort of artifacts that come just from the fact that learning simple mappings, let's say, with a nonlinear deep network is not always simple. And those artifacts will be introduced right away because it's so hard in your parameter space to reach that point where you have identity mapping. So this is another effect that kicks in and that can somehow remove those assumptions that even if your data is in a low dimensional regime and almost linear, it will be preserved in the output space of your network. So this is something really important to keep in mind as well.
So, Randall, I also noticed in about 2018, you were the first author on some really interesting work, and it was called a spline theory of deep learning. And then I think the next year it got into neurips. So I think I mean, I'm just reading a bit from the abstract. So you said you built a rigorous bridge between deep networks and approximation theory via spline functions and operators. And you actually think that this can explain a lot about deep learning in the sense of them being a composition of these max-affine spline operators. Has any of this work informed your view of deep learning now?
Yes, a lot actually. So I think, so first of all, I want to be precise that, of course, a lot of people knew about the fact that if you use, for example, ReLU activations, absolute value, and so on, or max pooling, then the whole network is continuous piecewise linear mapping. So what we did mostly is to make this a bit more rigorous and try to understand, okay, what the partition of the input space look like, what the per region mapping look like, and how can we use that to gain some more intuitions into what's happening. And the nice thing with this is that if you think about it, there is nothing simpler than piecewise linear mappings, right? Basically, it says that if you are in a region of your space, a region from the partition of your mapping, then the input-output mapping will stay linear. And this allows to do a lot of analysis, for example, to adversarial perturbation or all these type of things. And it can also open the door to other line of research. So, for example, one thing we did, I think it was NeurIPS last year or 2 years ago, was to use that to derive the exact expectation maximization algorithm for deep generative networks. Because now you have a cleaner, let's say, or simpler analytical form of your network. And this really opens to me the door to derive some more interesting theoretical result. It does not really help intuitively because I think everyone had this intuition from before already. But yeah, it's mostly a mathematical tool that allows to derive with more ease some interesting results. And I think one important thing as well is that you have really this dichotomy, right, between the, let's say, old school signal processing, template matching type of academia researchers, and the new school with deep learning, everything has to be trained and so on. And what is interesting in this paper is that we somehow bridge the two. We say that basically a deep net is a very smart way to build an adaptive spline, which will learn automatically its partition of the input space and the per region affine mapping, such that it works in high dimension. And this was not known before by anyone in the spline theory. If you speak about adaptive spline in high dimension, no one has no idea what to do except dimension 2 or 3 maybe, because a lot of PDE work uses. But outside of dimension 3, no one thinks about splines. So I think the very strong result is to bridge those two different fields.
That's fascinating. I think one of the issues, because I was speaking to Juan Bruno about this, and he was saying there was a big tradition in harmonic analysis of trying to reason about the behavior of these models. And we did have the universal function approximation theorem, which in a sense is talking about stacking basis functions, to approximate an arbitrary function. But you say in your abstract here that the spline partition of the input signal opens up in a new, opens up a new geometric avenue to study how deep neural networks organize signals in a hierarchical fashion. Because I don't think people really have much of an intuition on how these models behave and how to reason about them.
Yes, yeah, that's a very good point. So one thing that we did, for example, is to study how the partition of the mapping evolves as you go through the layers. And what we show is that at each layer, you keep subdividing your current partition. And this is very interesting because once you know that if you look at the binary classification, for example, you get that the decision boundary is basically linear in each region of the partition. And so what this tells you is that as you add layer, what you have to do is to refine the regions that still contain more than one class within them. And so this can really bring insights and maybe open the door to building new learning techniques to how many layers you should stack, which region should they subdivide, and so on. And this is really akin to decision trees and how they build their partition as well. So there is a lot of work that could be done also to maybe bridge the two or use one to understand the other. So, and it's really geometrical because it's in the whole field of computational geometry and so on, because you have those hyperplane arrangements, those half spaces, intersection of them, hyperplane tessellation, it's also known as this term. So it's really geometrical, and it can have a lot of interesting insights to understand what's happening. It also provides nice visualization tools.
It's really fascinating. It's straying from the. Would you be interested in coming back on the show for a future episode just dedicated to this topic?
Yeah, sure.
That'd be amazing.
Randall also actually released a paper called Neural Decision Trees. And in the abstract, it said they propose a synergistic melting of neural networks and decision trees that we call neural decision trees. So, this is something that you've been thinking about actually from many angles.
Mm-hmm. Yes. And that's very, very synergic to think about one from the point of view of the other as well, right? Because if you think of a decision tree, the real limitation of it is that how you subdivide one region by adding a node does not really tell you how to subdivide another region in another part of the space. So you don't have this, let's say, communication or friendly help between region subdivision. But in a deep net, what you do actually is that if you know how to subdivide one region, then it will automatically enforce how you subdivide nearby regions. And through this, suddenly you have a mechanism that appears, which is that you don't need samples in each region to know to subdivide them. You just need sample in some of the regions, and then it will guide you on how to subdivide regions of the space without samples. And that's something that is extremely strong when you go to high-dimensional settings, because you cannot have samples in all parts of the space by definition. So I think this is extremely nice to have both point of view, because then you can try to use the strengths of one to maybe improve the other. So that's really interesting to me.
I want to ask you this question that we ask a lot of our guests, because it's just, at least it's something that's of kind of profound interest to me, is that there is this apparent dichotomy between continuous and discrete. It's like the human brain is at the lowest possible level an analog kind of continuous system, and yet it evolved all these sort of discrete almost computations on top of it, like pulses that either fire or don't fire, like that type of thing. And in the learning world, or let's say really in the computation world, we have the fact that I can write a very short piece of symbolic code, discrete code, that can go and calculate the nth digit of pi or something like that. But it's almost impossible to train, or it is currently impossible to train any neural network of fixed depth to do the same thing. And so we have this weird, different regimes. We have the discrete kind of logic reasoning type world, and then we have the continuous differentiable type of world. Do you view those as, are they fundamentally different regimes, and we're always going to have hybrid systems that kind of combine both types of reasoning? Or is it possible to just say project that discrete computation fully into an analog type space if you just have enough, parameters or something?
Yeah, I think it really depends on the resources that you have, right? Because to me, at least, it seems that a hybrid system might be the most efficient, where you can easily, let's say, cluster different settings into groups, And then, and for this, you can just have a discrete settings. And then within each group, discretization is not good enough anymore, and you need to go into the continuous regime. So I think it will depend on the application you have at hand, or how efficient you want to be at doing it, either energy-wise or anything else. So
okay.
I think it's not clear if one should dominate the other necessarily. Like for example, if you go back to the spline setting of a deep net, you have a discrete setting, which is basically your partition, which region you are in. And then within that region, you have a linear transformation of the mapping, which is basically continuous. And both interact. If you adapt one, the other one change, and so on. And I think having this type of hybrid systems, and where somehow learning through the continuous part adapts the discrete part, is what is extremely powerful. And that's, I think, one extremely beautiful property of current networks, is that they do automatically this adaptive training of their discrete part through training of their continuous parameters. And that's why they are so efficient. Like if you think of pure approximation theory, and you have an adaptive spline in 1D, that's why you have the best convergence rate, basically. So I think you really need both systems to interact. If they don't interact, then I think it's really easy to become suboptimal and in an interesting regime.
Because we put a similar question to LeCun, and he was kind of saying that in an ideal world, we would have a discrete system as well. Humans are really bad at playing chess because we don't have that discrete system built in. But the problem I think people like LeCun have with these discrete systems is typically they're symbolic and they're statically coded. You could start talking about getting into a discrete program search, and you could even guide that program search based on some deep learning model. But I don't, to Keith's point, I don't think it's really possible to do that well inside the continuous domain, because if the problem even was learnable with stochastic gradient descent, the representation would be glitchy, right? It just wouldn't work.
Yeah, I think it depends a lot too on what are you trying to achieve with the model you build. If you just try to be as close as possible to, let's say, what the human brain is doing, then you might impose yourself to have some restriction on do you want it to be discrete or not. Or if you just want to have a model that you can deploy on a task and it can solve the task as best as you want. So I think, depending on what is your goal and what are you trying to imitate with the model would change how you answer that as well, right?
But what if the goal was task acquisition efficiency? So it's like, I don't know what the task is yet.
Yeah, I think that's again, to me, an hybrid system where you have interaction between both parts intuitively will be the most efficient. But yeah, it might not be true for all settings. So
when I was looking at Figure 3, both Tim and I were interested in the fact that if you look at the MNIST data, which to a human being is kind of a simpler data set, 1, 2, 3, we know how to do that type of thing, that as you increase dimensionality, it much more rapidly becomes extrapolation versus ImageNet, which seems to kind of more slowly transition from interpolation to extrapolation. And what I'm wondering is the intuition I got from that, and I wonder if this is completely wrong or it's correct, is that for machine learning, there's a sense in which MNIST is actually a harder problem because it has to look at kind of global relationships. Like it has to try and say, well, there's a circle over here that's kind of oriented with respect to a line that's kind of further away. And so it's harder for it to do that. Whereas we know that with like ImageNet, very frequently ML sort of devolves to looking at these micro texture, like, well, everything that has this shade of yellow is a school bus, type of thing. Is that an intuition one can take from that plot, or what does it mean that MNIST decreases so much more quickly?
Yes, so that's actually something that we try to clarify with the figure that comes after this one. Basically, the thing that you really need to be careful about and keep in mind is that if you look at, for example, a 16 by 16 patch for MNIST, you have basically maybe most of the information you need to solve the task at hand. You have a lot of texture about your digit, etc. If you look at ImageNet and you take a 16 by 16 patch, you have basically no information about the class. It's extremely small patch. It's almost constant across the spatial dimensions, right? It's basically a very small percentage of your full image. So that's why MNIST goes much more quickly to extrapolation regime for a fixed dimensionality in pixel space, because the information you have in that amount of dimensions is greater than for the ImageNet case. And this is only because it's already much more downsampled, right? If we were looking at MNIST, but with a 224 by 224 spatial dimension, and we look at a fixed dimensionality, then you will not have this difference anymore, and it might even reverse. So the really important thing to keep in mind is that even though it's the same dimension for both, it does not represent the same proportion of image that is present within that patch. Yeah. And that's why you have those differences in, that's mostly why you have those differences in those curves.
It's funny because we had the opposite intuition. And so in the following figure 4, you're showing then on MNIST that more of the variance is explained with fewer of the principal components on MNIST. And as you say, that's just because it's those pixels on MNIST are more salient for the problem. Just so I understand, because we were debating this a little bit, could you just give us your articulation of figure 4?
Yes, sure. So basically, what we are looking for the increasing dimensionality for the 3 dataset is we pick a number of dimensions in the spatial space. So we do this by extracting a patch, let's say. And then what we do is that we extract, of course, the same patch for all the samples. And then we are looking at the proportion of the test set patches that are in interpolation regime, and we report this. Now for the PCA plot, what we do is basically we look at, once you extract this patch, how many principal components you need to perfectly reconstruct those patches. Or you could say to explain the variance in those patches. And this gives a direct relationship because it shows how concentrated you are on lower dimensional manifolds, affine one, of course, that learns through the principal components. And it means that if you can encode much more information with much less principal components, then you lie on a lower dimensional affine manifold. And this, coupled with figure 1, shows that basically it's much easier to be in interpolation regime. So the whole point of using this PCA plot was to show how good a low-dimensional affine manifold represents the current extracted patches, and then to use this as a way to justify the extrapolation regime curves that we see. So because again, in the PCA regime, it's a linear manifold. So if only 2 components, for example, perfectly describe all your patches, then you will need very few training samples to be in an interpolation regime.
Okay, that makes sense. And then the staircase effect on the smooth subsample row is a function of the size of the Gaussian filter you use to smooth it?
Yeah, so the staircase occurs basically whenever the number of dimensions increase and we get a new bigger patch to get it. Because there is different ways. There is different ways to get it, right? One would be to always extract the center patch and remove some dimensions if you don't have an exact number of dimensions that you can represent with a squared patch. Another thing you could do is to first smooth subsample and then remove the dimensions. So there is different variants on how to extract those patches. We try to show 2 different ones to show that the results do not really depend on how you do this process. But you will have some little different artifacts like this. It does not change the overall trend, but it can change the small trends when you jump from one dimension to another.
But let me ask a question here about figure 4, again, about the intuition that we had on it, leaving aside interpolation and extrapolation for the moment. It seems that MNIST, for a given amount of variance explained and for a given dimensionality, MNIST requires more principal components.
For a given number of dimension, yeah. Because
if we fix the dimension and we fix the percent variance explain, MNIST requires more principal components than ImageNet.
Yeah.
That seems to me to tell me that MNIST is a more difficult problem. Is that not true?
I think it's a bit, so for a specific number of dimensions, you could argue that, but the thing you have to recall is that because MNIST images are much smaller in spatial dimensions, if you have a 16 by 16 patch, you have basically the whole MNIST dataset, let's say. And so just having a few principal components is not enough to really reconstruct the whole MNIST dataset. Now, on ImageNet, a 16 by 16 patch is almost a constant texture, right? You have a few different colors, but you don't have a lot of variation. It's basically through the spatial dimensions, it's basically constant. And what this means is that with only 3 or 4 principal components, basically one for each color channel, you can perfectly reconstruct all those 16 by 16 patches. So to really get to the conclusions you are saying, what you will have to do first is to either downsample ImageNet to be 28 by 28 or upsample MNIST to be 224 by 224. And if you if you do that, then basically I think you will have the roughly same evolution of the interpolation regime, because the 16 by 16 patch on this extra upsampled MNIST image will be either completely black or completely white. And in this case, you will still need a few principal components. So this is also something very interesting, right? Because it shows that maybe for the task at hand, you might not need to have such a high resolution image. You might downsample, but because when you downsample, you basically keep those crucial information, you don't necessarily go faster to an interpolation regime. So this is another point. It's really tricky. You should think of it as how much of the image do I encode given that number of dimensions. And then given that, this plot might make maybe easier to understand. 16 by 16
Okay, got it. Makes total sense.
Yeah, exactly. So 16 by 16 on MNIST is maybe, I don't know, 60, 70% of the image, while 16 by 16 on ImageNet is maybe, I don't know, maybe 5% of the image. And that's why you have those different regimes that appear.
Incredible. Randall, thank you so much for joining us this evening.
Sure. Yeah, thanks.
So
we just spoke with Randall. What was your take on that, Keith?
Absolutely brilliant. It was a true pleasure to speak with him. It cleared up a lot of thoughts and issues I was having with this paper. So for example, right up front, what he says is, my purpose behind this paper is to show that even though the intuition that people have of interpolation, like the intuition that we have of interpolation is good, the mathematical definition that we have of interpolation is not useful in high dimension. What I thought was interesting too is when we asked about, well, what about the manifold concept? Why isn't that sort of the definition of interpolation? And he brought up a really strong argument there, as he said, well, let's just take the simple case of suppose the problem you're trying to solve just is linear, like it just, everything is a linear data set, linear problem we're trying to solve. Like even in that case, this linear case, in high enough dimension, interpolation doesn't work. And there your manifold is just literally a convex hull, and so sure, you can have kind of a nonlinear transformation and a nonlinear shape and whatever, you're still hit by this curse of dimensionality. And he brought up the point that, like, of course, if your problem compresses down enough to where only a small number of transformed dimensions, right, latent space dimensions matter and everything, then you can be said that you're interpolating, because we're not really hit by that curse of dimensionality because we stripped away all the dimensionality down to these dimensions. We've gotten lucky. Our problem space, our data samples, etc., allowed us to do that. Okay, but that's not going to be all problems. Like some problems may just intrinsically have high dimensionality of interpolation that's not useful. So we need to do something better. We need to come up with a definition of interpolation that maintains the intuitive notion that we have of interpolation, but that continues to work in high dimension. And, and he made a very interesting kind of end goal here, which is like, if we can get a definition of interpolation that ends up approaching this concept of generalization, that's what we're trying to achieve, really.
And what do you think his take on generalization is then? Well, he made a comment that, on the one hand, you could just ridiculously sparsify the space and make it trivially separable, but then you lose generalization.
Well, yeah, and I think, because we did ask, or you asked, you put the question, what if the problem you're trying to solve is the ability to solve novel problems? Like, what happens then? Of course, that was in the context of our discussion about hybrid systems, where you're combining the continuous with discrete, and they're able to ping pong and kind of modify each other. And I think what we got from him there, and consistently, really throughout our discussion. And what's interesting is this totally aligns actually with Francois Chalet as well, which is that all these questions, like a lot of these very difficult questions that we're asking, are problem specific, and we don't currently have some one size fits all set of concepts that fits well for every problem space. It's very task specific, very problem specific, data specific. So I think that's an area where we got to dive deeper with him. But I didn't hear anything definitive, today.
It's a wrap. We just interviewed the godfather of deep learning.
How's that possible?
I think we can just quit now. We might as well just shut the channel down.
Yeah.
Obviously after we've published this.
It's the singularity.
So, what's your take, folks?
I think this, but we also interrupted him a little bit. Maybe the question was, I would have loved for him to be more a bit on like, where's the actual disagreement, right? Because a lot of times, when we put questions to him like, okay, other people say this, he was like, oh yeah, I agree, right? And it seems to be a general sentiment. That's also when we talk to other people about, perceived disagreements, they're always very, being good, being academics, being also friends probably with a lot of people. You always like, yeah, they have good point. We essentially agree on all the things, right? But then I sort of want to know where actually do people disagree, right? If it's that is a little bit, I obviously have a feeling, but it's still a little bit elusive, and if people disagree on the actual technical nature or more on the philosophical end of what does something mean, I definitely think there is, from hearing now, and I think from his answer to that question, I could hear a little bit in that he seems to be more optimistic on what these learning systems can do than maybe other people are, right? Because some people seem to have really kind of a hard stop on like, this will never be possible with like a learning system.
That's right.
Whereas it seemed that he had sort of a more optimistic outlook and said, of course they can't do it now, right? However, we work on it, we modify them, we're figuring out how do we need to build these systems such that, a learning system can conceivably, do many of the things that people would call kind of reasoning. And I think that's why he went into, let me give you an example of reasoning.
Well,
to sort of show, look here, here is an example of a reasoning that neural networks already do, and that means that something like reasoning in general isn't too far away, and that's ultimately where the disagreement might be with other people.
I think that was my take on his answer to our first question, like the why'd you write this paper, is I think, and maybe I gotta go back and watch this, but I think essentially what he was saying is, sometimes people, they have some definition in their mind, whatever it is, of interpolation and extrapolation. and they come up with kind of an argument to say, see, this machine learning is doing interpolation. And in a binary sense, it can't do extrapolation. And so therefore, there's this entire class of things, that it's not capable of doing. And I think that's what his objection was, which is, look, like, this is not a useful distinction to say between, it's not a useful distinction to draw between quote unquote interpolation and extrapolation. Like, here's an example of a definition, right? That's a relatively standard definition of interpolation. And if we apply this interpolation to theoretically what machine learning is doing and empirically to what machine learning is doing, it's always extrapolating. So I think that's what he's objecting to, is just like, look, don't come to some strong conclusion about what machine learning neural networks, I'm not sure what the right way to phrase things is now, what it's capable of doing. Like, we just need to do more work to expand its capabilities.
Folks like Gary Marcus making this case of we need discrete models because they can abstract broadly. They give a couple of examples, binary encoding for numbers. And there's one example with, can you have a model that reverses the bits? Or I think there was another example in his algebraic mind, which was about, can you generalize from the even numbers to the odd numbers? And you can't do that. And the reason you can't do it is the new examples are completely outside of the training space of the input data. And probably that problem is not interpolative, or it's not differentiable. I mean, Walid Subbers says the same thing. He says in language processing in particular, like in language understanding, in order to have broad generalization, you need to have abstract rules. So, for example, being able to generalize from Mary loves John to Mary loves Jane, they make the argument that with a statistical approach, that just wouldn't be possible.
Well, I think, and this is just my opinion, but I think his answer to my digits of pi question kind of shed some light on what his position is on this, which is that it's too early to, theoretically and scientifically, for us to make that determination. Like, because he said, look, okay, people have only been able to calculate digits of pi, like within the last 100 years or whatever. I'm not talking, like, we're not there yet. I'm not talking about that class of problems. I'm talking about these
prime numbers as well.
Right. So I'm talking about these things like a cat jumping up here. And so some of these examples that Gary Marcus may bring up may fall into that, even though they seem simple, okay, they seem deceptively simple, they may still fall in the bucket of these kind of much more towards the discrete spectrum of capabilities, which we can't currently do with our methods and of machine learning, but we're going to continue to get closer to that end of the spectrum. And so it's premature to say that, like, machine learning, and again, whatever you conceive that to be, neural networks, whatever, will never be able to get there. Like, he and Yann is optimistic that we'll be able to get there. I'm not as optimistic. I think there is there's just a qualitative difference between, structural, topological, discrete reasoning and continuous differentiable reasoning. And I don't know how we're ever going to get that gap bridged. He brought up some methods to think about, but.
Right. But the key question is whether it's possible at all. And there was an article by a guy called Andrew Yee, I think, and it really annoyed Yann LeCun. And he said, look, people are still making the argument that neural networks interpolate. And in that article, he was basically saying, well, neural networks are a little bit like a Taylor series approximation. You take a function and you just kind of approximate it, inside a certain range, and then it goes haywire outside of the range. Francois Chollet came on the podcast and he said, look, it's a little bit like in Fourier analysis when you try and you kind of like, you take these little sines and cosines and you fit it to a discrete function and it's glitchy, right? And actually, if you look at harmonic analysis, this is what Juan Brunner said on the show, on the geometric show. He said that, well, a neural network, even the universal function approximation theorem, it's all about stacking these basis functions together, right, to kind of approximate some target function. Well, if that's all neural networks do, how could they possibly generalize?
Look, I don't want to use the word like generalize. I don't know that. What I would say is this, which is that no matter how discrete in appearance the human brain is, all the signals that neurons generate, receive, whatever, at the end of the day are continuous functions. I mean, they're, a charge that has a continuous function. Now, somehow or another, like the brain and its structure does take that continuous analog, I should have said analog, probably a better word, but it takes that analog computational environment and produces digital reasoning. So I don't think it's beyond that. Like, I just don't see how anyone could reach the conclusion that it will be impossible, like, to do discrete reasoning with neural networks. I think it's just a question of, like, for me, I think it's more of a question, is that the efficient way to do it? Like, if you fast forward 2,000 years from now, when people have figured out all these problems and we have, like, AIs walking around killing us or working for us, whatever the thing may be, are they going to be using a neural network for everything? Or is it going to be a neural network with, some classic digital compute components with some other stuff, like a hybrid kind of structural system that does things, I think is more what I'm asking.
Like LeCun and Hinton, they of course, that's what I was going to say. They have, like, nature on their side, in that no matter how much we cut open the human brain, we don't find, like, a discrete computer in there. Like, of course, the individual neural spikes are discrete, like there's either charge or no charge, but there is, like, continuous release of neurotransmitter. So I agree, like, the brain is like a very continuous distributed machine, and there's no discrete thing in there. There's no part of the brain where it's like, look, one brainy packety.
He said that, and there is a level at which that's true, which is there's a spike train, and we can kind of recognize a spike because it's a maximum in this analog dimension. But my point is, that's still an underlying analog dimension, and so I don't see why, in principle, you couldn't build a neural network that has, like, these kind of continuous values, but still ends up with something that synthesizes a discrete decision.
Sure, but wouldn't it be glitchy and it still wouldn't extrapolate?
I have no idea, like, what I just don't know. I think this kind of the point is we're too early on to reach these conclusions that it cannot be done. I do sort of feel that it's just not the efficient way to do it, that we're going to end up with a case where we're going to have systems that have analog continuous chunks that are neural networks or whatever, and we're also going to overlay that with digital computation that's implemented by the typical kind of digital computer. That's going to be these hybrid systems working together, just like you brought up with, hey, look, Alpha Zero, AlphaGo, all those things can be viewed in the same kind of hybrid way, right?
But that's exactly, I mean, you said, this is what you said, and also when he said, like, so first when he said, we're far away from that with the digits of pi and so on, but also when he said, humans are actually pretty bad at chess or at discrete exploration in general, and that's how humans do it, right? Humans build discrete reasoning on top of this sort of neural continuous function, and it's actually really hard. Like, to do discrete reasoning in your head, you can do it slowly, and you have to do it deliberately with attention. If you do, like, multiplication of 5-digit number in your head, right? This is not a oh my gut feeling. This is like you sit there and you have to, like, keep all this stuff.
It's not a hash table lookup, like the multiplying numbers up to 10.
And we can build children's toys like that for like 20 cents that multiply 10-digit numbers easily, right? So I think this is
we teach children
the point
both ways. We teach them hash table lookup, like memorize, all the numbers from 1 to 100 multiplied or something, and then we teach them an algorithm. We teach them the discrete iterative thing, and we teach them hash table lookup.
And this is built on if you build this discrete reasoning, you can probably build it on top of these models, right? But yes, is it the most efficient way to do it? Maybe not, right? But then again, if you do it, if you manage to do
you can train it differentially.
You seem, at least from the perspective of humans, you seem to have something insanely powerful, right? Because, if you just have a discrete algorithm, you have the algorithm. But if you have if you've actually managed to train a discrete algorithm on top of this continuous function, it will be able to sort of learn in the same continuous way that a neural network learns, but it will be sort of be able to self-modify its discrete algorithm, and that, I think, I agree. I'd also be in the maybe longer term future positive that might be possible.
But I think that's because I said to him, do you think AlphaGo is a good thing? Do you think it's a good thing to have a kind of discrete search which is guided by a neural network? And he didn't like it, and I assume he didn't like it for the reason you just said, Yannick, which is that the discrete part of it is hard coded and it's been told to do a specific task. It's not learning. I think LeCun would rather have something which is entirely differentiable, right? So because LeCun wants learning end to end in a neural network, right? Yeah. And also it's almost like he was saying before, well, humans can't do discrete reasoning, so it would actually be a more sophisticated form of intelligence if we had discrete reasoning. But do we necessarily even want that in our models, or is it just the fact that he wants it in the models, but he wants it to be differentiable and learnable as part of the main model?
I think so, because that's where he got with the the critic, actor-critic type models. I think
if people nowadays talk about differentiable, they always talk about like single shot feed forward. Like, I input something into the machine and out comes a prediction. Whereas he also makes a lot of arguments for, this energy minimization, which means that essentially at test time, at inference time, I do a minimization algorithm. And, when he talked about reasoning, he was mentioning that as an example, as essentially saying, look, I have my trained neural network, and now at inference time, I actually still perform an algorithm on top of that to minimize some energy function, given my trained model of the world, let's say. So I think we might be able to make that more learned by also learning the algorithm that we do at inference time. But I don't necessarily think that he's talking about, we need to end-to-end learn like a machine where you simply input something and then out pops through forward prop, pops an answer.
But all of these things are just reasoning by the back door. It's even with actor critic, as I understand, that's just the way of hacking the value, the advantage function, right? With some, I'm not an expert in reinforcement learning, but I think that's what it is. The same thing with the energy minimization.
Yeah, I kind of agree with you there.
But the energy minimization has this particular thing of this idea, which I think today is underexplored, to actually do something at inference time, like to not just forward prop. And that I feel it's underexplored nowadays.
No, I agree with you there too. But I think sometimes I feel like this is feature creep in a sense. It's like, we have neural networks and we know what deep learning is, and some people now want that to be redefined as just a general purpose research paradigm that includes all possible things that we can do with machines or chemicals. It's like, what use is that? Like, what use is it defining, all types of computation as differentiable computation? Like, we lose some ability to talk about these in sort of a sane way. That was kind of like what I was saying, look, allowing for a variable number of layers in a neural network, that's discrete computation, right? That's not differentiable training. Nobody knows how to train in an arbitrarily unbounded number of layers in some differentiable way, right?
But there's the neural ODE stuff.
Well, all those types of things run into big training problems. Things become really hard to train when you have these types of essentially discrete, transitions, right? Or combinatorial kinds of transitions. And this is classic stuff. This is really classic stuff. It's like, even if you try to do mixed integer optimization, right? So you have a problem that has some combination of integer variables, discrete variables, and some combination of continuous variables. There's all kinds of hacks to try to do that in differentiable ways. They don't, in general, arrive at the optimal discrete solution. Like, you do some continuous stuff, and then at the end you kind of discretize it in one way or another, and you wind up with a solution that's kind of approximately correct, but you're not guaranteed that you're going to find the one that's actually correct if you discretely combinatorially examine that space, right?
Can we finish by talking about a couple of things? So first of all, there's table 1 and the structure of the latent.
Table 1 is the biggest argument against the most prevalent argument against this paper. Sorry for the triple negative. But when the paper starts out by saying, we build a convex hull of the training data. If your point is not in the convex hull, not interpolating. And then people go, wait, but you're talking about the input space of data. You're talking about the pixel space. And, for sure, we're not talking about the pixel space because, the neural network is, their data manifold and woo-hoo-hoo-hoo. But we're talking about, if you go to the last layer, to the latent space before the classification, it's just a linear classification. There, in that space, we're talking about interpolation, right? There is where the neural networks interpolate. And this experiment clearly shows okay, it might be a rigid definition of interpolation, but it clearly shows no, even in that space on a trained ResNet, there is no interpolation going on. As soon as you pick 30 dimensions or more, it's all outside of the convex hull of training
right
data.
But this gets to the punchline, right? Because Keith was going to ask a really cool question, which is imagine it was a very small latent and it was interpolating, and then what if you up projected it to 1024 dimensions, and that would that suddenly now be extrapolating, right? So we almost need to have an information theoretic way of looking at this. But anyway, my intuition is that deep learning models encode the most high frequency information into the latent space, right? And this information would be encoded in a minimally distributed way to denoise the predictive task, which is to say, right, there's a few dimensions of the latent, which should be encoding the actual things that you've trained it on. So my intuition is actually most of the dimensions of the latent are kind of just encoding low frequency information, so you can discard them, right? And I know you said the other day, well, maybe the whole point of neural networks is they're a distributed representation. So maybe they are distributed over all of the layers, over all of the dimensions in the latent.
I mean, I would actually argue not that neural networks are putting the data in a minimally distributed way, but in a maximally.
Why?
I think just my intuition is that if I were a neural network and I had all of these dimensions at my disposal, I would encode lots of information redundantly. If it were too much space, I would encode the same information pretty much redundantly in many of the dimensions that I could.
But that's noisy, right? So you're taking a softmax, and if you're noisily aggregating over all of those features, that you don't want to do that.
Yeah, but still, if I have backprop, right, and the backprop path goes through each of the dimensions. So for each of the dimensions, I'm asking myself, how can I change this one to make my prediction even better, right? And it doesn't matter if over there one of the dimensions is already doing the classification for me, right? The nature of backprop means that, I'm going to every single dimension independently and deciding how can I change this one to make it even better. So that's why I think lots of information, if the latent is too big, lots of information will be encoded redundantly.
But that's the key right there, is if the latent is too big. And so this is where all the pruning literature comes into, which is that the majority of the time people are running neural networks in situations where the latent space is too big. They're just, we just flat out have far too many, far too large of a latent space. And so even though it may be encoded, densely there, it may be putting all kind of little bits of extra information, it's probably only adding little plus or minus, 0.1% type things to the accuracy. Whereas, and so since it is only adding these little kind of very tiny values there, right? The only meaningful way to talk about interpolation or extrapolation, because you've only got little bits of stuff you're using on that entire dimension that you've added there, is really more just, are you interpolating on the most salient dimensions? Which is, again, back to my question about why are we concerned with whether or not every single dimension falls within the sample range?
Yeah, exactly. But there's a few things there. I mean, it's really good that you bring up sparsity. I think that's fantastic that you brought that in, because, as you say, most of that information is redundant. But then what Yannick was saying was interesting. does distributing all that information rather than, because my intuition is it increases noise, but actually I think Yannick's saying it increases precision.
But in a very tiny, like it's a tiny contribution. So let's suppose the latent space is not too large, right? Like if the latent space is not too large, in other words, let's say it's just barely big enough to classify your images. And let's suppose you're doing multi-class. So we've got 10 classes, and we just barely got enough latent space for it. My intuition would tell me that if those classes are somewhat different from one another, like we're classifying brown dogs from white dogs from like every other, simple kind of dog, but they're different from each other and it's not easy to determine, which is which, and just a guess, is that probably what would happen is you would find that, these 5 bits are kind of the ones that tell you whether something is a dog, and these 7 bits tell you if it's a duck, and these 4 bits tell you if it's a gun, and these 5 bits tell you if it's an image of the sky. Like I would guess that it would end up encoding it that way, since they don't have a lot in common. You can't really use entanglement like too much, except for a few dimensions. There might be some overlaps, but
yeah, I think what people mean a little bit is when they start going down the interpolation road is that we've played with GPT-3 as well, right? And then you do something with it, you enter something, and in some places you're like, I see how you did that, right? You just took that newspaper article and you just kind of replaced some stuff in it, right? Like you sort of, whereas if you were to talk to like a human, you'd sort of, like that stuff wouldn't happen as much. Even, and then, of course there's the argument. I think people that say, well, it's just interpolating, or it might also be, it's just sort of repeating the stuff in the training data. I think what they'd like to see is more like the pattern that these models extract aren't sufficiently high level for them, right? And I think the entire discussion is, can we get to arbitrary high abstractive levels of pattern recognition with such models if we engineer them, train them in the correct way? Or is there I guess some fundamental limitation to that? And yeah, as we said, that the answer might be quite far off. As for the number of latent dimensions and so on, I mean I agree with Keith. I think having a big latent space and also having big weights and so on might be more of a necessity for training than it really is for encoding. Like it appears to help if we have lots of weights to train, such that sort of we get to combinatorically try out combinations of weights, only few of which might ultimately end up being important, right? That's kind of a lottery hypothesis sort of way of going down. So yeah, I agree, most of the information ultimately might be only contributing a little bit, right? But my intuition would be that, this is kind of, because it's kind of redundant information, right? Because it's like, I'm encoding this over here. I'm also encoding it in like a tiny little different way over here, or some add-on or some uncertainty or some one training sample is a bit different. So I'm going to put that right here.
Mm-hmm.
Yeah, that's fascinating what you said about Frankel's work, though. I never really heard you articulate it like that, but it's actually kind of like a search problem rather than a learning problem. What you're doing is you're giving it all of the possible, you give a random initialization on a densely connected network and you're saying, just go and find the ones that work rather than create it from first principles.
Yeah, that's why initializations are so important, right? Yeah. Is because you sort of try, like your initialization essentially is your buffet for SGD to like choose a good one from to then go ahead and refine.
But how much refining is it? Is it more finding things that already work versus refining?
Yeah, it's well, same, but what it is not is sort of learning from scratch.
Right.
Yeah.
That's what, like, people like you cannot initialize a neural network from zeros and then have it learn well, at least not today. Maybe that's gonna come in some form, but initialization is actually pretty important.
It's pretty crazy, isn't it?
And
that's a crazy thought.
And that's like one hint that, you know, we're never essentially training from scratch. We're sort of training, we're sort of giving the choice of many combinations of good weights or of semi-good weights, and it has to pick sort of the good ones to continue.
Yeah, exactly. It's already pre-trained. You just don't know which.
Ha! Yeah, I mean, the argument, a little bit of the argument against that is in sort of the evolutionary approach, where you say, you know, you can make the argument, you know, humans have sort of developed these abilities to reason, to recognize super high level patterns while only having a continuous brain. But then the other side of this is, yeah, but it's not like a single human that has achieved that, right? It's not like one single learning system that has achieved that, but it's actually like this evolutionary system, which is in essence a massively distributed combinatorial trial and error search, right? And that is not a learning system, so to say, as we imagine it today. At the end, you end up with a learning result, but the evolutionary algorithm is way different than we imagine learning.
It's not even all humans that have learned it. It's all, you know, individuals of all tens of millions of species that have ever lived on Earth that have learned this, right? Which is pretty much like the lottery ticket hypothesis. Let's just randomly train crap tons of weights and then slowly prune them and see what happens.
Right.
Brilliant. Well, gentlemen, it's been an absolute pleasure. I guess we'll make this a Christmas special. I mean, it is pretty special.
Oh yeah.
Let's be honest. So
this is the end. Worn the
hat.
Goodbye. We're gonna sign off.
Nice meeting you.
Check out.
Indeed. But thanks for bearing with us, folks. We have had a couple of months off. I've had a bit of a break, and you know the guys have had a bit of a break. So yeah, we're back.
Good to see you all again.
Peace out.